Let's go like this. I wonder if this one will show up a little better. Yeah. It's about the same. Yep. Bruh. Keep saying unregistered. It's fine though. Let's see. Okay. Reverse delete algorithm. What the frick is that? Let's just watch a YouTube video on this.
Now, if you're watching this video, you already know about Kruskal's algorithm. This is called the reverse delete algorithm, and it's kind of Kruskal's in reverse, and I really kind of like it. So the steps really easy to follow. So all we need to do is delete the largest edge, check that the graph is still connected. If it is, keep repeating that loop until the edges equal the vertices minus 1. So to do that, I've got a graph and an exact copy of that graph. And on this exact copy, I'm going to do my deleting. So, what's the largest edge? Well, 9's the largest edge. I'm going to delete that. And then I say to myself, is the graph still connected? Are all the vertices still connected by a road, by an edge? Yes. Okay. Repeat. Delete the largest edge. 8's quite a large edge. Let's delete that one. Are all the vertices still connected? Yes, they are. Okay, what can I delete? 7 is a large one, so let's delete that. Okay, are all the vertices still connected? Yes, there's no orphans, there's no one all by themselves, so we can keep going. Okay, what about the 6s? All right, can I delete
2 6s?
6? Let's give it a try. Is everything still connected?
There's 3 of them.
Yes, everything's still connected. What about this 6? Why don't I delete that? Is everything still connected? Uh-oh. F and E have been cut away from the group. So I'm going to have to put that back. I've made a mistake. Control-Z, undo. Here's a 6 back again. Okay, let's find another large edge and delete that. 6. Can I delete 6? Okay. Everything's still connected? Okay, looks good so far. Now, if I was to delete 5, everything would be disconnected, so something's happening there. Repeat until edges equal vertices minus 1. All right, let's see. 1, 2, 3, 4, 5, 6 vertices. 1, 2, 3, 4, 5 edges. I have created a minimum spanning tree using the reverse delete algorithm. Now, if that feels like Kruskal's in reverse, it's Kruskal's in reverse. I really like it. It's really neat. It's a really nice way to come up with a minimum spanning tree. Definitely give it a try.
Yeah, that makes sense. I can do that, I think. Okay. So, let's see. Edge 1 is greater than the cost of edge 1 is greater than or equal to the cost of edge 1. I don't like this unregistered thing. It's throwing me off. I'm not spending $4 so we get rid of that. So what's the yeah. So first we're gonna want to look at. I think we want to sort this first. Um, yeah, so let's do that. There's an easier way to do this, I think. So I like a table button actually. What is this? Text. It's like an image thing. Okay. Let's actually not close it just yet. So we're gonna want label this. Uh, so we'll do I and the edge at I. Uh, we'll need some space, and then okay. And probably just like this. So okay, so then we're gonna want to start with the highest edge. So in iteration one, we're gonna have DE. So um oh, I totally forgot a row. Fuck. This isn't a big deal actually. I can just do a bunch. This. The count of that edge, and then we can just do same thing. Wait, what is this? Is T prime disconnected? Oh, okay. So iteration one here. Already determined we're gonna have DE. Um, and the count, the cost limit is gonna be 13, and then edges in T at the end of iteration I. T is gonna be, so edges in T. So you take, so it's just if it's still connected, so it goes from the tree minus and this edge, so you take you get rid of this edge, and then and at the end you just return T. Okay, we just remove the edge. It is done. Okay, so to the list all the edges. Uh, so Um, okay. I guess I'll just list them in case in order. So we'll have C, um, CD, and then AC, and then um, BC, BE, CF, AB, and DF. And this is disconnected. No. Okay, so now in the second iteration, we're gonna want to take out CD. So CD, so it cost 11, and then we're gonna have left AC, BC, BE, um, CF, AB, and DF. And this is still connected, so no. Then, how, like, how far am I supposed to go? Um, okay, it's okay. Alright, so let's see. Um, Okay. Alright, that makes sense. So then let's see. Okay. Next, we're gonna look at 11 AC. You see the cost here is 10, and we're gonna be left with BC, BE, CF, AB, and DF. And if you, yeah, let me open this in Paint. So um, so we've gotten this, this, this. Okay. Hold on. Let me do it in black. This. Is there? Uh, whatever. So got rid of this one. We got rid of this one. And this one. So then, nope. Where? So next we're gonna look at BC, and the cost on this one is 9. And then we'll have BE, CF, AB, and DF. Let's see. So if we get rid of this one, now these ones don't have a path to these ones, so it would be yes. Okay. No, I think we still just go through this. So in this iteration, we're going to be looking at we'll be looking at BE. Yeah. So we'll look at BE, and then BE has a thing of 8, cost of 8, and think I'll just keep the same list, so yeah. F, A, B, F, and these will be the same. And then the next time we're going to be looking at C and F. So CF and CF have a thing of, so we can erase this. CF have a thing of 7. And since nothing's changing, the edges in T are going to be the same. So we can just write BE. I think we can actually just take this lasso tool and go like this. Like, that's the easiest way to do this. Like this. Copy and paste. And then we can just erase this part. Paste. Be, I think one more. Okay, so that should save us some time. This is gonna be yes. Next one we're gonna be looking at is gonna be A, B, and DNF. A, B, DNF. So A, B, nothing here. We already know that's CF doesn't have anything. And DNF. But so CF AB at a cost of 6. This one has a cost of 7 or 5. Yes, and yes. Okay. Let's just go ahead and erase this much. Go ahead and close this box. Like this. And boom. I think that's good. Okay. Pretty happy with that, I think. Close this Not say that. Okay, let's get to the next question. Okay, so this one has 3 parts. So let's see. Um, Minimum spanning trays by bottle rolling packages. Runs Prim's algorithm to find the resulting graph. He routes the internet packages between the nodes in the industry. However, he did not like running programs, and for nobody could understand, was adamant about never writing MST algorithm covered in the algorithms course again. But I suppose the original network was a graph with vertices, edges, and weights, and the resulting span tree was um, a tree with vertices, edge prime, and W prime. Note, Joey can still use the blue rule and the red rule, just not on the whole graph, as that corresponds to the greedy algorithm we discussed in class. Oof, this is hard. So okay, so this is the resulting graph. Can still use the blue rule and the red rule, just not on the whole graph. So that corresponds to the greedy algorithm. Um, okay. Um, I mean, you have to give pseudocode too. Frick that. Hold on. Control Shift T. This thing again. Frick, bro. Um, I don't know how do you add how to handle adding unknown to AMST. My God, that's just straight doxing me, bro. Just accept all the cookies. So, okay. Um, Someone asked this 12 years ago. Bro, I am not reading all of this to figure this shit out. Okay. Um, Cusco's algorithm there too. So, any edges? Okay, let's just do this for now because I don't need that screen for right now. Um, um, Okay. Let's see it. Let's see. Let's see. Can I just like Google this? Oh, it's just on Chegg. uh, what is this posted? This is from 16 hours ago. So someone recently put this on there. Interesting. Wait. I think. Come on. I think at the end of the class, maybe we talked about something similar. Um, Oh yeah, I need to figure out what the frick this is.
So let's begin by talking about what union find does. Imagine if you had some objects and you want to group them together according to some criteria. So one such grouping might be this. Now, once you have completed the grouping, you would want to know certain properties about the groups, such as how many groups there are, and if two objects belong to the same group. The union find data structure, as its name suggests, supports two operations. The first one is called union, which takes as input two elements, x and y, from the set of objects, and it joins or unions the groups containing x and y. For example, we can start with 0 and 2 belonging to the same group, and 1 and 3 belong to the same group, and when we call this function union 0, 1, it joins or unions the groups containing 0 and 1. So the final result will be all four objects belonging to the same group. The next operation is called find, and it takes a single object x as the input and returns the group that x belongs to. So now let's see how we can implement union find. We will first walk through the ideas and discuss the code at the end. Union find is useful in graph type problems. So our first step will be to cast the grouping in the form of a graph. And the way we do that is to connect all the objects that belong to the same group with an edge, like so. Now, remember we need to find a way to determine which group each element is in. To do so, we designate a representative element for each group. This element will represent the entire group it belongs to, in the sense that the find function will always return the representative. For example, when we call find of 4, the representative of the group that 4 belongs to is 0, so therefore we return 0. And of course, the representative will return itself. As another example, when we call find of 2, we return the representative of the group 2 belongs to, which is 5. Notice that two elements belong to the same group if and only if they have the same representative. So the representative provides a way of checking if two elements belong to the same group. So now we need to implement the other function, which allows the union of two groups. And to do that, let me rearrange this graph in a suggestive way. I've now put the
Let me get a different union find algorithm. This guy does a pretty good job. And this guy.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve number of connected components in an undirected graph. And yes, this is once again a problem from our blind 75 list. The link to this spreadsheet will be in the description if you want to take a look. You can see about 18 people are currently viewing it, including me. So this is a problem, problem 34 from that list, number of connected components. So this is the graph one we'll be solving today. Probably tomorrow I'll finally go ahead and do Alien Dictionary. So the main reason I've been putting off Alien Dictionary and even this problem is because I couldn't really find a free version of these problems on the website leetcode. So I actually went ahead and shelled out the $35 for a leetcode monthly premium subscription. So for the next 30 days, I will have LeetCode Premium. So if you have any premium problems that you want to suggest, feel free to do that in the description. Big shout out to my Patreon supporters for making this possible. But yeah, so now let's actually get into the problems. So we're given a graph of n nodes, pretty simple so far. So the number of nodes will be given to us with an integer n, and we're also just given an array of edges belonging to this graph. Every edge is undirected. It connects two nodes A and B together. And all we need to do is just return the number of connected components in the graph. Now, what is a connected component? You probably already know, but it's basically just an individual portion of the graph that's all contiguous. See how everything in this portion is connected? We also have a second portion, which is disjoint, right? So these two components are disjoint, right? They are not connected to each other, but each of them separately is connected, right? Like every of these 3 nodes is connected together. These 2 nodes are connected together. Therefore, we have 2 different contiguous components. So there's not a lot of edge cases with this problem. It's pretty straightforward. So for example, if we were just given 2 nodes, 0, 2, no edges between them, then we would just return the number of nodes we're given. 2 nodes, therefore we have 2 connected components, right? 1 node by itself does count as a connected component. And of course, if we're not given any nodes, n equals 0, then we return 0. But clearly, this is pretty straightforward so far. So there's a couple of ways to solve this problem. So we're given the edges as a list of edges, but we could make an adjacency list, which would make it easy to do a DFS search on the entire graph. So that's one way to solve this problem. Just go through every single node starting at 0, right? So we start at 0, then do a DFS search from here. So we're going to mark 0 as visited. We're going to see, okay, we can reach a 1, mark that as visited. From the 1, we can reach a 2, mark that as visited. So far, we've only done 1 DFS search, right? So therefore, we found 1 connected component. Now we are then going to try to do a DFS starting from 1, right? But what we're going to find is that's already been visited. So we don't want to add that to the number of connected components, right? So far, we still only have 1 connected component. We can do the same exact thing for second node. For node number 2, it's already been visited. No need to increment the number of connected components. Then we're going to get to node 3. This one has not been visited. Therefore, now we have 2 connected components. So now let's just do a DFS on here to mark all of them visited. 3 is visited. It has 1 neighbor 4. 4 is visited. And then there's none left. So we got 2 connected components. We'll try to do a DFS from 4, but it's already been visited. So therefore, we, in the end, notice we only had 2 connected components. Now, this isn't a bad algorithm at all. The overall time complexity is basically going to be, big O of E plus V, because notice we are going to have to go through every single edge when we traverse the graph and when we actually build the adjacency list. And we're also going to have to go through every node, iterating through it as we traverse the graph and as we, try to do a DFS starting at every single position. So this is going to be the overall time complexity. Not bad at all. But there actually happens to be a more natural way to solve this problem, and if you have heard of the algorithm called union find, it's a pretty rare algorithm to need on LeetCode, but if you do know this algorithm, then you basically know that this algorithm was literally made for a problem like this, literally made to be able to count connected components, as well as to be able to identify, disjoint sets and all that stuff. So I'm going to use this problem as an opportunity to go over union find once again. I think I've done this once before in a previous problem, but let's dive into this. So we're going to mainly be maintaining 2 arrays, one called the parent array, and we're going to have a value in that array for each node that we're given in the input. And initially, the array is just going to look like this, 0, 1, 2, 3, 4. So each index, so the index 0 represents the 0 node, index 1 represents the 1 node, and the value in every single array clearly matches that of every single node initially, at least. So initially they do match. What that basically means is each node is the parent of itself. So the way union find works, it's basically a forest of trees. So we're going to have multiple trees. Initially, clearly we have n trees, one for every single node in the input. And as we go through every single edge, such as 0 and 1, what we're going to do is take, let's say 0 is going to be the parent, so 0 is a parent of itself, but what we're going to do to 1 is say, no, 1's parent now is going to be 0. Basically, what we're doing is just connecting the 2 nodes, right? And since we know that we just made a single connection, what we can say now is that, we started out with 5 different connected components. We just merged 2 of them. Every time we perform a merge, we're basically taking the number of connected components we have, decrementing it by 1. So that's how we can keep track of the connected components. And there's one slight it's non-required, but it's an optimization that's pretty easy to make with this problem. We're going to maintain the rank of every single component. So basically for every single node, we're going to maintain what's the size of it. Basically, if this is the parent, what's the size of its entire connected component? Right now, what we would initially for each of them, it's obviously going to be 1, right? The size for all of them is going to be 1 initially, but since we just made this merge, we're going to leave the rank of 1 as it is because it's not the parent. But for the parent 0, we can say, its rank is now not 1, it's actually going to be 2. Really, we're just talking about the size if this was the parent, which it is the parent, right? So in our rank array, we could change the first 1 into a 2. And the reason we're maintaining this rank is basically just an optimization. So right now, you can clearly see we have one component of size 2 and we have one component of size 1. If we were merging these two, right, would we want to merge this one as a child of this one? If we did that, we would get something like this, right? We'd get 1 and then 0, right? We'd get basically a linked list. So why would we do that when we would rather merge the smaller connected component underneath the bigger one? So if we do that, we'll get something like this, right? And clearly here you can see if this was a tree, the height of the tree is now minimized. Before we had a tree that was basically a linked list. Now we have a tree that's actually kind of a binary tree. If you adjust your head by 90 degrees, you can kind of see what I'm talking about. But so that's the main algorithm. So far we've just done the first edge. So now let's look at the second edge in our input, 1 and 2. So we're connecting 1 and 2. And the way we're going to merge these is first we're going to get the root parent of both of these. So for 2 itself is its parent, but for 1 has another parent, 0. So when you get the root parent of 2 nodes, that's how you know if they're already connected or not. Because if maybe this 2 was connected to 1, then we would say, okay, 2's parent is 1, 1's parent is 0, and then what we would say is, okay, 1 and 0 both have the same root parent, so therefore they're already merged, so we don't need to merge them again. But in this case, you can see 2 has its own 2 is the parent of itself, 1 has a root parent of 0, so therefore they're not connected.
Thanks,
so we
Jurgen.
can connect them together. We can union these 2 components together. So this one is larger, this one is smaller. So we're going to add this as a child of 0, where we're always adding to the root parent, right? We're not going to add it to 1, we're going to add it to 0, even though this edge is connecting these 2 together. When we add that edge itself, we're going to make sure that 2 is connected to the root parent because we want to minimize the height of the tree. And once we do that, we know
This is
that the rank of
not
this is
seem like
actually
what I
going to...
need.
Okay, let's talk about a really neat application of the union find, which is Kruskall's minimum spanning tree algorithm. So you might be asking yourself, what is a minimum spanning tree? So if we're given some graph with some vertices and some edges, the minimum spanning tree is a subset of the edges which connects to all the vertices and does so at a minimal cost. So if this is our graph with some edges and some vertices, then a possible minimum spanning tree is the following and has edge weight 14, well, total edge weight 14. Note that the minimum spanning tree is not necessarily unique, so if there is another minimum spanning tree, it will also have a total weight of 14. So how does it work? So we can break it up into 3 steps essentially. So the first step is easy. Just take all our edges and sort them by ascending edge weight. Next thing we want to do is we want to walk through the sorted edges and compare the 2 nodes that the edge belongs to. And if the nodes already belong to the same group, then we want to ignore it because it'll create a cycle in our minimum spanning tree, which we don't want. Otherwise, we want to unify the 2 groups those nodes belong to and keep going. And we keep doing this process until either we run out of edges or all the vertices have been unified into one big group. And you'll soon see what I mean by a group, which is when our union find data structure is going to come into play. So if this is our graph, then to run Kruskall's algorithm on it, first let's scale the edges and sort them. So on the left side, you see I have all the edges and their edge weights sorted in ascending order. So next we're going to start processing the edges one at a time, starting with the top, so I to j. So I've highlighted the edge I to j in orange, and you can see that it connects nodes I and j. I and j currently don't belong to any group. So I'm going to unify them together into group orange. Next is edge A to E. So A to E don't belong to any group, so I'm going to unify them together into group purple. Next is C to I. So I belongs to group orange, but C doesn't have a group yet, so C can go into group orange. Alright, E to F. F doesn't belong to a group, so F can go to group purple. Next, H and G. Neither H nor G belong to a group, so I'm going to say you guys belong to the red group. Next, we have D to B. They also don't belong to a group, so give them their own group. Let's say group green. Alright, and now I believe this is when things start to get interesting. Now we're trying to connect C to J, but notice that C and J already both belong to group orange, so we don't want to include that edge because it's going to create a cycle, so ignore it. And to check that they belong to the same group, we would use the find operation in our union find to check what group they belong to. So this is when the union find really comes into play. Next is edge D to E. So note that E belongs to group purple and D belongs to group green. So now we want to merge them together because they don't belong to the same group. So either the purple group's going to become the green group or the green group's going to become the purple group. It doesn't really matter. So now we would merge them, and this is when the union operation in our union find becomes useful. It allows us to merge groups of colors together very efficiently, and that's the important note. Next edge would be D to H. H belongs to group red, and D to purple, so merge the groups together. Let's say they both become group purple. Next up, we want to add edge A to D, but A to D already belong to the same group, so that would create a cycle. So we don't want to include that edge, so skip it. Next, we want to include edge B to C. B to C belong to different groups, so merge the two groups into one larger group. So we have found the minimum spanning tree using Kruskal's minimum spanning tree algorithm. Pretty neat, right? So the underlying data structure which allows us to do this is the union find. It allows us to merge groups of colors together efficiently, but also to find out which groups nodes belong to, so that we don't create a cycle. So that's Kruskal's algorithm. It's super simple, given that you know how the union find works. So I'm going to go into some detail in the next video explaining how the find and the union operations work internally and how we can actually implement it in some useful way. Alright.
Okay, but this still doesn't really like tell me how to solve this problem. If you add it, um, oh no, we'll have to skip this part. This time a physical cable between two nodes in the MST got damaged. Bro, I don't know how to do this shit. Self-inflicted, nobody's forcing him not to. This time a cable that was not in the tree was damaged and replaced by a much faster cable, thus decreasing Okay. Okay, I'm gonna need to go. I think I need to learn more in class before I can solve these. So, in the meantime, I'm just gonna study up on other stuff. So yeah, it's like firstly, let's just go through this. Just download this and then just open it in this tab so that y'all can see it. So let's take this off. So what we can do is let's go through. So I have the homework 2 solutions here and the homework, and then here's the lecture. Let's go through this. Okay, so let's do this. Let's do this way. So let's just create a new document and call it midterm study. Term 1 study. Let's create this puppy, and then so it's gonna be homework 2. And so let's start with this. So extra. So big O is like upper bound. This is lower bound, and this is like middle bound, I think. So I need some music, I think.
this video we will talk about an alternative definition of asymptotic notations. So before we go further, let's summarize what we know. So the first notation, the first asymptotic notation is theta notation, and if f is equal to theta of g, then we can say that growth rate of f as well as g are similar. If f is equal to big O of g, then we can say that f grows no faster than g, right? And in other words, g is asymptotic upper bound on f. And similarly, if f is equal to big omega of g, then we can say that f grows at least as fast as g. In other words, g is asymptotic lower bound on f. Okay, so now what we do, we try to convert this definition, this formal definitions, in terms of limit. So from this, if we focus on this particular ratio f of n upon g of n, then from this definition it's clear that if f of n upon g of n is some constant term, then we can say that f is nothing but theta of g. So that particular thing is corresponding to very first definition of theta in terms of limit. But the main thing here is, if you can notice, then the symbol is implication, not double implication. That means this is not if and only if condition. There may be some function for which this limit does not exist, but still f of n is equal to theta of g of n. So therefore we can't generalize this, but we can check this. Like for example, let me take one example, then it will become more clear. So let's say my function f is this phi n square plus 6n plus 7, and let's say g of n is equal to n square. Okay, and now I want to apply the very first definition of limit. So the idea is, let me find out what is f of n upon g of n. So in this particular case, it's phi n square plus 6n plus 7 upon n square. If I simplify this further, then I will get this phi upon 6 by n plus 7 by n square. And now if I apply limit, and again, why I am considering limit n tends to infinity, because as per our assumption, we are interested in very large values of n, right? So if we do this, then the answer will be 5, right? So what is the meaning of this? The growth rate of f of n is approximately 5 times as compared to g of n. And since this is a constant term, if what we can do, if I take g of n upon f of n, then also I will get the constant term, so 1 by 5. So therefore we can say that f is nothing but theta of g, in this particular case phi n square. So the conclusion is, from this, because we are getting this particular constant term which is not 0 or infinity, we can say that f of n belongs to or equal to theta of n square. Okay, now intuitively we can also see why the second and third definition is also true, because if g of n is dominating term as compared to f of n, then our limit will be 0, and at that time we can say that f is nothing but big O of g of n. So that is all about this particular second definition. And third definition, again, if f of n is a dominating term is compared to g of n, then limit n tends to infinity, f of n upon g of n will be infinity, right? So at that time we can say that f is at least g, right? So that is the idea of this 3 definitions. So let me take one more example. So now let's say my function is, let's say, n square, and I want to compare this function with, let's say, g of n, which is nothing but n cube. And again I will use this particular definition, limit n tends to infinity, f of n upon g of n, which is nothing but this, so which is nothing but limit n tends to infinity So here if we simplify this, then we will get limit n tends to infinity 1 upon n, and after further simplification we can say that the value of this particular limit is 0. So now if we compare these two functions, then we can say that definitely g of n is dominating as compared to f of n, so we can write f of n is equal to big O of g of n, which is nothing but f of n is equal to big O of n cube. So now let me take one more example, and now I'm changing the roles of f of n and g of n here. So instead of considering f of n is equal to n square, let me take f of n is equal to n cube and g of n is equal to, let's say, n square. And now again I will apply the same limit n tends to infinity f of n upon g of n, and after simplification, as you know, we will get limit n tends to infinity n cube upon n square, which is nothing but limit n tends to infinity n, so which is nothing but infinity, right? So we can say that f is dominating term. In other words, value of f is at least g of n, so that we can write f of n is nothing but big omega of g of n. So far I've used the word definition, but actually this is not the definition of asymptotic notations. The actual definition you already know, which we have discussed previously. Here, as you can see, the implication is in just forward direction. There is no double implication. So I recommend you to first apply formal definition, and if you are stuck, then only you can use this trick of limits. And the main idea here, more often you will encounter that this particular ratio of this type, infinity upon infinity, and then you can apply L'Hospital rule and solve this very quickly. So that is the main idea of this video. Thank you. Subscribe to my channel for more videos. Hello friends.
Okay, so for this video today, we are going to have a discussion about asymptotic bounding and bounding the asymptotic nature of our functions. So I always say things like O of n or n squared, but what do I really mean? I kind of addressed this in another video where I talked about what asymptotic functions actually mean and what these boundings mean, but I think it's time to go very deep into this topic and get very detailed and mathematically rigorous about what I'm actually saying. So before I continue on, if you have not subscribed to the channel, subscribe to the channel and like this video. My goal is to make this one of the world's largest video where I talked about what asymptotic functions actually mean and what these boundings mean, but I think
Yeah, let me start from the page.
Okay, so what we're gonna discuss today is asymptotic bounding. It's very important for algorithms, and this is generally something that if you don't have a sound fundamental understanding of, you're going to be mistaken in an interview. You're going to say a complexity that's completely wrong. Again, if you have not subscribed to the channel, subscribe to the channel, like this video. So, when we see a single for loop, doesn't that mean linear time? When we see two for loops, doesn't that mean quadratic time, right? Not always. So I think what we have to look at first is a little math and a little calculus. I was never amazing at calculus, but to really understand asymptotic behavior, we need to look at what asymptotic really means. So what does asymptotic behavior really mean? So I have a graph here. So what is this graph? So maybe I don't know the equation for this graph, but I can tell about where this graph is going. So if I took the limit as x approaches infinity, if I go towards infinity, where does the y value go? And you see that the y value goes towards 0. So this is what this looks like. Okay, so now we see the asymptotic behavior of the graph of 1 over x, which is what this graph is. This is the graph of 1 over x. The asymptotic behavior of it is that as x approaches infinity, we get closer and closer to 0. And do you notice our points of interest? What we're interested in here is tail behavior. The idea of asymptotics and looking at an asymptotic behavior is we want to see how does the graph behave getting into very, very large x values, into very large values. This is the idea of asymptotic complexity. Okay, so now we know what asymptotic means. It means tail behavior, but wait, why don't I just measure the elapsed real time? Why don't I just take the wall time? Why don't I just do that? Why don't I just do what I see in LeetCode? I mean, I run my code on LeetCode, and it tells me this ran in this many milliseconds. So I guess I know how strong my algorithm is, right? So that is not the best way to approach things. So in computer science, often problems are applied at a grand scale. Like if you're writing an algorithm for a company like Facebook or a large company, it's going to be used across millions and millions of users and large inputs to an algorithm. So our best point of interest is to see how does this behave on the tail end? How does this behave as input gets very large? We only see the true measure of performance of an algorithm when we have very, very large input. And this is why asymptotic complexity intrigues us in computer science. So let's look at an example to really drill this in. So we have an algorithm insertion sort that is going to do 2 times n squared comparisons. So this could be any random implementation, and for some reason it does 2 times n squared comparisons. So we have a merge sort implementation that does 50 times n log n comparisons. So we know that insertion sort is slower, and don't worry about the constants here, they're just arbitrarily chosen. So we have computer A running the slower algorithm insertion sort, but computer A second. And we have computer B running the faster algorithm, but computer B is 1,000 times slower than computer A. It is 1,000 times slower, but it's running a faster algorithm. So what is the approximate wall time going to be for both of these computers, computer A and computer B? Okay, so can you guess them now? Now, do we have an idea of which is going to be faster? Okay, so we see that the actual running time for the faster computer is going to take 5.5 hours and is running a slower algorithm. And we see that computer B is 1,000 times slower. It is 1,000 times slower, but it's going to only take 20 minutes to run. So why was this algorithm faster? And why was this algorithm slower? Why did the slower algorithm lose on a computer that is 1,000 times faster? So the answer to that question lies in the idea of asymptotic bounding and looking at asymptotic behavior. So I think something to really drill in this concept is looking at linear time, looking at the class of boundings that we call linear time. So whenever I say linear time, I say this in a lot of videos, I say we're going to have a linear time bound. What does that actually mean? So I want us to look at a few different graphs. So what we're going to do is, I'm going to draw a few graphs, and we're going to notice something in common between them, and it's going to lead us to the most critical word in all of that we're doing. So let me start drawing graphs. So here is our first graph. Y equals 1 over 2x. Okay, so we have one graph. So let's draw another graph. Okay, so here is another graph. We see that this is the graph of y equals x. So let's draw 2 more graphs just to really hammer this point home. Okay, so I just drew the graph y equals 2x. And I just drew the graph y equals 3x. So what do you notice about these graphs? I want you to mentally imagine this. If I zoom out, when our input is super, super, super large, when I zoom far outwards, what are all of these going to do? What will they all look like? Do you see how all of these are lines? Do you see how all of these are lines? All of them have the same tail behavior. All of these graphs have the same behavior. So the key thing behind asymptotic complexity is The whole point of taking asymptotic measures is so that we know how a graph is behaving when input is very large. When input is very large, that is when we see a graph's true colors. So do you see why we drop constants? If I have a big O of 1/2 of n, so why do I drop the 1/2? Why does it just become big O of n? Why is big O of n an asymptotic measure? So you see, this is the exact reason, because all of these graphs will do the same thing when we get very, very large input. They will scale in a linear fashion. This is a linear scaling. When I say log n time, when I say linear time, when I say quadratic time, when I say cubic time, when I say factorial time, when I say exponential time, what am I saying? I'm not describing an individual graph, I am describing a class of functions. I am describing a class of behaviors. And that is what this is all about. Okay, and that is all for this video. If you like this video, if this video was clear, if this made things a little clearer about why we
Yeah, this is a good video. Okay, I did not look at that. Let's go back to this video.
It's time to go very deep into this topic and get very detailed and mathematically rigorous about what I'm actually saying. So before I continue on, if you have not subscribed to the channel, subscribe to the channel and like this video. My goal is to make this one of the world's largest software engineering resources for preparing for interviews, and this is a very large component of that, understanding how to bound asymptotically. So first, let's look at our most common bound, which is the upper bound, which is the big O bound. And we're going to look at the mathematical understanding behind it, and I will make it as simple as possible so that we can really understand what we're actually saying when I say big O of n. So, okay, the way that asymptotic bounds work, and the way you really should think about this, is every time you have a piece of code or you have an algorithm, it requires resources. These resources come in the form of taking up time or taking up space. And our job is to analyze how much time and space does this algorithm take, because that is of interest to us. The more we can understand how an algorithm behaves, the better we can optimize it, see where its flaws are, see where we can improve things, and we can improve its asymptotic nature. So first of all, I keep saying the word asymptotic. What does that mean? So asymptotic, as you probably are familiar with the concept of asymptotes, is the nature of a graph or a nature of a function as it reaches a untouchable bound, as it reaches a very large value, it approaches a certain value, right? So it's about the nature for n's that are arbitrarily large, n's that are very, very, very large, beyond what you could even imagine, because when we see how a function behaves on the tail end, on the asymptotic end, that is when we have a true understanding of its performance. Because some algorithms might run faster initially, we might have a curve running like that, and then we might have a line running like that. Initially the curve is faster or slower, but on the tail end is when we see who really wins. So enough talking about this, let's see an actual definition. So first what we need to see is we need to understand the work we're doing. So let's define a function. It's normally called t of n for the work that our function does. Okay, so we have t of n right there. So this is either the time or the space a function takes as n changes. Do you see how n is the parameter to the function? As we modulate n, I can move n up or I can move n down. When I do that, the output of that function changes. And our job is to bound the change in that function, bounds the possibility of how this function can change as n gets very large. So you'll see what I mean. We have our function of how things change versus how we modulate n. So now what we need to do is establish the definition for big O. And we'll get into the other bounds, but let's just look at big O, which is the upper bound. Okay, so let's look at the rigorous mathematical definition for big O, which is an upper bound. It's upper bounding work. So let's read this verbatim and see what it means, see if it makes any sense. T of n is bounded, upper bounded, by f of n if and only if t of n is less than or equal to some constant c times f of n, the function we chose to bound with, for all n greater than the initial n, or n naught. So does this make sense? To me, it really doesn't make sense. This is the definition that we get in our introductory classes. This is the definition we get when we first learn it. And this is too thick for me to understand. So why don't we break it down and really see what this is suggesting to us? So first, what this is actually saying to us, what it's proposing is we have a certain amount of work. We're doing a certain amount of work given by the function t of n. That's our actual graph. That's the actual work the algorithm does. We want to bound it. We want to put a bound over it, a cover over it, and we'll see what that looks like using a function called f of n. So we say t of n can be upper bounded, big O, upper bounded by f of n. And what are the conditions? How do we know that f of n satisfies? How do we know that f of n can upper bound us? Okay, are you still with me? So we only can declare this is true if and only if this is true. The function that we have, if we multiply our bounding function, f of n, by some constant, we will be able to always keep t of n under our bounding function. So let me show you. This is an example, and this doesn't need to make sense right now, but it will make sense once I do this example. So our job is to choose a c so that f of n bounds t of n, our actual work. So let's do a bounding right now so you see exactly what I mean. Okay, so now what we're gonna do is we're gonna explore bounding. We're gonna do and try to satisfy what that guy just told us. So here's t of n, here's our function. And what I want to do is I want to choose a class of functions. We know our class of functions of how we can bound. Well, we'll become familiar with them over time, but we want to bound this somehow. So why don't I start with trying to bound this? So let me define a function that might bound this. Maybe it might bound it, maybe it might not. Let's try it right now. Okay, so here is our function t of n, and I made a random choice. I said, I want to try to bound with n squared. So our function we want to try to bound our work with is n squared. So we see n squared. This is the raw function of n squared multiplied by c being 1. Okay, so what we're doing is c times our function is going to be the result of the function we're trying to bound with. Stay with me. This will make sense in a little. And now here is the critical point. Am I able to modulate this base function of n squared so that for all values of a constant I need to find, this t of n stays under it? So why don't we go crazy? Why don't we turn c to 100? And now let me change our graph. Okay, and now is this true? If I take all n values on this axis and I go from n naught, which might be 0, all the way to the end, far away, will t of n always stay below this function? And what you see here is, it looks like it will. This guy's diverging off to here, he's going to stay linear, and what we see is, this is a correct bounding. This is an upper bound. We have satisfied the rules that Big O imposed on us because we found our constant. We found a constant c that keeps t of n below the bounding function. What is the bounding function? The bounding function is n squared. So what can I declare right now? So what I can now declare is that this function is upper bounded by n squared as long as I can choose some multiple c. I just proved I can choose a multiple c that will keep this function t of n below me at all times. But do you see a problem with this? Do you see a problem of choosing n squared? I mean, this looks like a linear graph. We're familiar with linear time. Don't you think we could improve on our upper bounding? So this brings me to my next concept of how tight is our bound? How tight is our bound? So this is something that is always to be considered. When we're trying to bound something, we want to be as accurate as possible to not have all this extra wasted space above the function. When we're bounding, we want to be as tight and exact as possible to what the function's going to do on the tail end. So while
this is
big
kind
O
of
of n.
Alright, I'm just saying, so so here what they do is for this top function, so I'm about to crash out. So it just zooms in for both of them, bro. Fuck that. So just like this. So I take 3n plus 1, put that on the top, and then I put the O of 3n on the bottom. And this turns into 3, which is equal to 3 because you can just get rid of this shit. And these are closely bounded. So it becomes 3 to the power of n. And for this one, be thing as O of 3 of n. So you take the 3 of n, you put that one on top. 3 to the power of 3n. So is 3 to the power upper bounded by 3n would be no. Right? So 3 of n is lower bounded by 3n and okay. That makes sense. That explanation where you can just say upper bounded or lower bounded is big. Makes so much sense. Okay. Give me 1 sec. I'm gonna go throw some rice in a rice cooker. Be right back. I'm hungry, so have this. Also, I found out you can press Windows tab and it'll only show tabs in like your monitors. You can't see my other monitors, but I can see the tabs in my other monitors, so it's just pretty cool. So you can go like this. But if I were to press Alt tab, it would show all of them, all my open tabs. But then press Windows tab, it only shows the 2 on your monitor. Anyways, yeah, I'll be right back. I'm gonna go put some rice in my rice cooker. So let's see. Right. Okay, so now I think I can solve the rest. So suppose that then so for the first one, what we would do, let me just write this on paper on the iPad here. So the first one, what we would do is we would take this big ass fraction thing, it's n3, n to the power of 3 plus the sine of n plus 1 all over n squared plus n plus 1 all over n squared. Honestly, I forget what to do when you get a problem like this. Okay. So let's see. We can just math calculator with steps. Microsoft came up with the thing. Yeah. Because of like calculus probably. Yeah, so it would be the limit of as n approaches infinity. How do I type infinity in there? It's like infinity? Yeah. And then the whole thing is gonna be n to the power 5 plus n to the power 3 plus the sine n plus 1, and then it's gonna be all of this divided by n squared to the power 2 plus n squared plus n plus 1, and then it's going to be all of this. It's going to be like, how do I select everything? It's going to be all of this divided by n to the power 2. Alright, send that. Okay, well, that's cool. I'll just plug it in the ChatGPT. 2. Okay, wait. I just want to have chat like go through all these. Um, okay, let's just put this in here. So that you guys can see. So wait, no, it's this one. Let's analyze the given function. So g of n is this. So I think it's well, hold on. I think it's to the power um so it just simplifies to become the n2, so it just becomes simplifies to become n to the power of 3. So then for the first one, when you look to see if it's a lower bound of this, since g of n grows at least as fast, is lower bounded by, yes, so that's true since these are the same. This is true, that makes sense. And since O of n is upper bounded by this, so that means it's true. Nope. So then it's all of them. Okay, that makes sense. That makes perfect sense. So now we gotta do this part. So let's see. Okay. So what is the worst case running time of the following pseudocode notation? Suppose that all arithmetic take constant amount of time. Justify your answer. So worst case, so you start with an array of length n, and then yeah, that's just the data. So the result is return scalar val. Okay. For I, from 1 to n squared, j is equal to 1, and while j is less than or equal to I squared, do this. So how would you do this? So the let's see. So for 2, it would be the summation. The outer loop would be from I equals 1 to n squared, and within there, how would you write this? It would be, well, j is less than I squared. I don't know. Let me see. So, wait, what? T. Wait, what? Control Shift T. There you go. So then, oh, the log in. Let's do that real quick. Okay, so let's just put this image in there and see what it says. Okay, so the inner loop, the while loops is from while j is less than I squared. For a given value I, the number of iterations in the inner loop is I squared. Therefore, the number of iterations in j depends on the value of I and can represent it as I squared. Of j is that okay? It'd be easier for us. So the number of iterations of I j depends on I squared on what I is. So to I squared. Okay. Determining we need to use the sum of squares formula. When do you learn this? Okay, so this is like a statistics shit. What is this?
Hey everybody, the purpose of this video is to hopefully explain to you all why a least squares regression line is called a least squares regression line. So what I've got here is 5 points in the coordinate plane. I put them all
This is
in the
what I
first
need.
quadrant to make them easy.
But basically, I just need to remember that it's from the summation of I for I squared. Okay. And then you have to run the sum of squares formula. But I don't think I'm gonna have to know to remember how to do the sum of squares formula. And then you find that the worst case is closely bound by ourselves. Okay. Okay. I need to focus. I'm losing concentration. Okay. So this next one. Well, let me look at the explanation that the teachers give for problem 2. Okay, so let's do this one. So grade length n 0 equals the value for I to n. So it's gonna be summation from I equals 1 to n, and then for ln natural log of I. So what would it just be? Natural log of I. Would it be like this? Be another summation of from j equals 1 to the natural log of I, and within here we're gonna take actually I have no idea. What do they do? So important to notice that the assignment includes experimentation by n as shown below. Yeah, that's what I was confused by. Since experimentation by n inherently contains n multiplication operations of the total time is O of n, must spend time calculating the value. Now consider the outer loop, which goes from 1 to n. This will be the base of summation. The inner loop do we need to write out the summation? Yeah. So say I should study like half the content, and then on Saturday I'll do the other half. No, on Friday I'll do the other half. On Saturday I'll just do practice tests all day. Monday I'll do more practice tests and go to office hours, and then Tuesday's the test. So okay, got this. Got this. So I need to get to the section 3 as well after I get this done. Yeah. Okay, so let's try this first. So first see it. This one is too hard. I got a question mark here. I don't know how you get to that answer. So the outer loop is the summation from I equals 1 to n, and within here we're doing, well, I is less than or equal to I, j times 3. So found, this is just, we can skip this, this is fucking, this O1. This is every third iteration of I. So this would just be, log 3 of I think. Yeah, it's, well, it's less than, let's turn on the size of I, so it'd be O log of I, log base 3 of I. I think that's what it would be. So okay. Okay, so what's the explanation? So all assignments are basic. Outer loop is from 1 to n, so that's the basis of the summation. Yep. Inner loop iterates from 1 to I, but is indexed by multiplying by the previous index by 3 each time. Okay, so then inner loop is O of log there. Yeah, this is what I ended up with. So right now the summation will be log 1 plus the log of 2 plus the log of n factorial. And the additional log x plus log y equals log xy, which is y log 1 plus. Oh yeah, that's true. This term is n log n, meaning the quantum complexity of the algorithm is theta n log n. Okay. The n factorial over k factorial times n minus 1k factorial nk, which is equal to 1 over nk, which means it's about theta of nk. So this is going to oscillate between 1 and 3. Um, so I think these can, using logarithmic rules, this can be pushed to the front. And then log n, so this one would be this would be lower bounded by log n, I think. Oh, it would be, it's closely bounded. This is gonna oscillate between 1 and 9 for all n is less than. Um, so it's gonna be n cubed plus 2n squared plus 5. So this is just n cubed. This is just gonna be closely bounded. It's just gonna be theta. Yeah, that's easy one. So this would be 2n is omega of 3n, right? Wait, what? Oh, it's 2 to the power of n. So this is gonna be lower bound. Is this gonna be omega of n to the power of 3? So what's the explanation here? N log n for n squared is equal to 0. N log n is equal to 0, 1. This is gonna be tightly bounded. Um, it's gonna be what? If k has to be greater than 2, this one doesn't make sense to me. Um, okay, I think I got that down basically for the most part. It's an acceptable degree for a test. I mean, I'll do more review later. Okay, what else do we have? Well, they do upload the solutions. Here. Okay. So let's look at some graphs. Let's try to understand all this stuff on here. Definitions and applications. So a graph, easy. Path. Okay, got all this easy. Okay. Connected and does not contain a cycle. Okay. Okay. Some so BFS algorithm proof. Is there like a Harvard lecture or something, anything like that? Oh yeah, let's get at it. So yeah, let's just watch this algorithm. I mean this freaking lecture.
The following content is provided under a creative.
So this is like the full class.
The following content.
So let's just start. Let's just look at this one. I got this one.
Content is provided under a
Wait.
Creative Commons license.
This one.
Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Today we're going to sort of introduce graph search in general and talk about one algorithm, which is breadth first search, and understand how, in principle, you could solve a puzzle like the Rubik's Cube. So before I get to Rubik's Cubes, let me remind you of some
I'm just gonna take notes
basic
on this.
stuff about graphs. Or I can tell you, to start out with, graph search is about exploring a graph. And there's many different notions of exploring a graph. Maybe I give you some node in a graph S and some other node in a graph T, and I'd like to find a path. That's going to represent a problem like I give you a particular state of a Rubik's Cube, and I want to know, is there some path that gets me into a solved state? I really want to solve this on stage. What the hell? We started. All right, so this is a particularly easy state to solve, which is why I set it up this way. All right, so there you go. 7 by 7 by 7 Rubik's Cube solved in 10 seconds. Amazing. New world record. So that you're given some initial state of the Rubik's Cube. You're given the target state. You know what solve looks like. You want to find this path. Maybe you want to find all paths from S. Maybe you just want to explore all the nodes in a graph that you can reach from S. Maybe you want to explore all the nodes in a graph, or maybe all the edges in the graph. These are all exploration problems. They're all going to be solved by algorithms for this class and next class. So before we go further, though, I should remind you what a graph is and sort of basic features of graphs that we're going to be using. This is all 604.2 material, so you should know it very well. If you don't, there's an appendix in the textbook about it. We have a set of vertices. We have a set of edges. Okay, edges are either unordered pairs, so sets of two items, or ordered pairs. In this case, we call the graph undirected. In this case, we call the graph directed. Usually, there's only one type. Either all the edges are directed or all the edges are undirected. There is a study of graphs that have both, but we are not doing that here. So, some simple examples. Here's a graph. This is an undirected graph. This is a directed graph. Okay, set of vertices here is ABCD. Set of vertices here is ABC. Set of edges here is E. Is going to be things like AB, BC, CD. I think you get the idea. Just for completeness, V is ABCD, just so you remember notation and so on. One of the issues we're going to talk about in this class is how do you represent a graph like this for an algorithm? So it's all fine to say, oh, this is a set of things, this is a set of things. An obvious representation is you have a list or an array of vertices. You have an array of edges. Each edge knows its two endpoints. That would be a horrible representation for a graph, because if you're, I don't know, you're at vertex A and you want to know, well, what are the neighbors of A, B, and C? You'd have to go through the entire edge list to figure out the neighbors of A. So spend linear time just to know where you can go from A. So we're not going to use that representation. We're going to use some better representations, something called adjacency lists. Cool. Okay, over here you've got things like AC, BC, and CB, so you can have edges in both directions. What am I missing? BA. So that's E in that case. There are a whole lot of applications of graph search. I'll make you a list, talk about a few of them. So we've got web crawling. Your Google, you want to find all the pages on the web. Most people don't just tell you, hey, I got a new page, please index it. You have to just keep following links. In the early days of the web, this was a big deal. Following links, finding everything that's out there. It's a little bit of an issue because if you define it wrong, the internet is infinite.
Let me go get some food.
Dynamically generated pages.
I think my rice is done cooking by now. Let me go check on it. Okay, let's see. Okay, is it? Okay, I'm back. But is it have some like tuna rice mix thing here? Is it okay to eat fish every day? That people eat fish twice a week? Yeah, but how is there too much? Uh this shouldn't be getting my information from Reddit and said it's Harvard. Uh Pregnant women and children should avoid fish. Alright. I should be chilling. Is it okay to eat eggs every day? I eat eggs every day.
But to deal with that, Google goes sort of breadth first. For the most part, it's prioritized. But you want to see all the things you can reach from pages you already have and keep going. At some point, you give up when you run out of time. Social networking. You're on Facebook, use Friend Finder. It tries to find the friends that are nearest to you, or friends of friends is sort of a level 2 search. That's essentially a graph search problem. You want to know what's 2 levels or 3 levels of separation from you. And then you loop over those and look for other signs that you might be good friends. You're on a network, like the internet or some intranet. You want to broadcast a message. So here's you. You want to send data out. That's essentially a graph exploration problem. That message, that packet is going to explore the graph. Garbage collection. I hope you all know that modern languages have garbage collection. This is why you don't have to worry about freeing things. Even in Python, even in CPython, I learned, there is a garbage collector as a version 2. But also in PyPy and Jython and in Java and like pretty much every fairly modern language, you have garbage collection, meaning if there's some data that's unreachable from So you have your variables, whatever is actively in variables that can be accessed by the program. Everything that's reachable from there you have to keep, but if some data structure becomes no longer reachable, you can throw it away and regain memory. And so that's happening behind the scenes all the time, and the way it's being done is with a breadth-first search, which is what we're going to talk about today. Another one, model checking. Model checking is you have some finite model of either a piece of code or a circuit, a chip, whatever. You want to prove that it actually does what you think it does. And so you've drawn a graph, which is, the graph is all the possible states that your circuit or your computer program could reach, or that it could possibly have. You start in some initial state, and you want to know, among all the states that you can reach, does it have some property? And so you need to visit all the vertices that are reachable from a particular place to do that, and usually people do that using breadth-first search. I use breadth-first search a lot myself to check mathematical conjectures. So if you're a mathematician and you think something is true, like maybe, well, it's hard to give an example of that, but you can imagine some graph of all the possible sort of inputs to that theorem, and you need to check them for every possible input. This is true. Typical way to do that is breadth-first searching through that entire graph of states. Usually we're testing finite special cases of a general conjecture, but if we find a counterexample, we're done. Don't have to work on it anymore. If we don't find a counterexample, then we have to do the mathematics. So doesn't solve everything, but it's helpful. And then the fun thing we're going to talk about a little bit today is if you want to solve something like a 2x2x2 Rubik's Cube, optimally, you can do that using breadth-first search, and you're going to do that on your problem set. Solving this one optimally using breadth-first search would definitely take more than the lifetime of the universe. So don't try 7x7x7. Leave that to the cubing experts, I guess. No, I think no one will ever solve a 7x7x7 Rubik's Cube optimally. But there are ways to find a solution, just not the best one. OK, so let me tell you just for fun, as an example, this pocket cube, which is 2x2x2 Rubik's Cube. What we have in mind is it's called the configuration graph, or sometimes configuration space, but it's a graph, so I'll call it a graph. This graph has a vertex for each possible state of the cube. So this is a state. A little creaky here. This is a state. This is a state. This is a state. Now I'm hopelessly lost. Okay. Anyone want to work on this board? No one? All right. I'll leave it unsolved then. OK, so all those are vertices. There's actually a lot of vertices. There are 264 million vertices or so. If you want, as an aside here, number of vertices is something like 8 factorial times 3 to the 8. And one way to see that is to draw a 2x2x2 Rubik's Cube. So these are, these guys are, these are what you might call cubelets or cubies, I think is the standard term in Rubik's Cube land. And so there's 8 of them in a 2x2x2, 2 cubed. You can essentially permute those cubies within the cube however you like. That's 8 factorial. And then each of them has 3 possible twists. It could be like this, it could be like this, or it could be like this. Okay, so you've got 3 for each, and this is actually an accurate count. You're not overcounting the number of configurations. All of those are, at least in principle, conceivable. If you take apart the cube, you can reassemble it in each of those states, and that number is about 264 million. Okay, which is not so bad for computers. You could search that. Life is a little bit easier. You get to divide by 24 because there's 24 symmetries of the cube, 8 times 3. You can divide by 3 also because only a third of the configuration space is actually reachable. If you're not allowed to take the parts apart, you have to get there by a motion. You can only get to 1/3 of the 2 by 2 by 2. So it's a little bit smaller than that if you're actually doing a breadth first search, which is what you're going to be doing on your problem set. But in any case, it's feasible. Okay, that was vertices. I should talk about edges. For every move takes you from one configuration to another. You could traverse it in one direction, make that move. You could also undo that move. Because every move is undoable in a Rubik's Cube, this graph is undirected. Or you can think of it as every edge works in both directions. So this is a move. It's called a quarter twist. It's a controversy, if you will. Some people allow a whole half twist as a single move. Whether you define that as a single move or a double move, not that big a deal. Just changes some of the answers. But you're still exploring essentially the same graph. So that's the graph, and you'd like to know some properties about it. So let me draw a picture of the graph. I'm not going to draw all 264 million vertices, but in particular, there's the solved state. We kind of care about that one, where all the colors are aligned. Then there's all of the configurations you could reach by one move. So these are the possible moves from solved state. And then from those configurations, there's more places you can go. Maybe there's multiple ways to get to the same node. Okay, but these would be all of the configurations you can reach in 2 moves. Okay, and so on. And at some point, you run out of graph. So there might be some ways to get, there might be a few things, few nodes out here. These are kind of the way I'm drawing this. This is everything you can reach in 1 move, and 2 moves, and 3 moves. At the end, this would be 11 moves if you allow half twists. And I guess as puzzlers, we're particularly interested in this number, which you would call, as a graph theorist, the diameter of the graph. Puzzlers call it God's number. If you were God or some omni-something being, you have the optimal algorithm for solving the Rubik's Cube. How many moves do you need if you always follow the best path? And the answer is, in the worst case, 11. So we're interested in the worst case of the best algorithm. For 2 by 2 by 2, the answer is 11. For 3 by 3 by 3, the answer is 20. That was just proved last summer with a couple years of computer time. For 4 by 4 by 4, I don't have one here. I think we'll never know the answer. For 5 by 5 by 5, we'll never know the answer. For 6, for 7, same deal. But for 2 by 2 by 2, you can compute it. You will compute it on your problem set. And it's kind of nice to know because it says whatever configuration I'm in, I can solve it in 11 moves. But the best known way to compute it is basically to construct this graph one layer at a time until you're done, and then you know what the diameter is. The trouble is, in between here, this grows exponentially. At some point, it decreases a little bit. But getting over that exponential hump is really hard. And for 3 by 3 by 3, they used a lot of tricks to speed up the algorithm. But in the end, it's essentially a breadth first search. What's a breadth first search? This going layer by layer. So we're going to formalize that in a moment. But that is the problem. So just for fun, any guesses what the right answer is for an n by n by n Rubik's Cube. What's the diameter? Not an exact answer, because I think we'll never know the exact answer. But if I want theta something, what do you think the something is? How many people here have solved a Rubik's Cube? Ever? Okay, so you know what we're talking about here. Most people have worked on it. If you think about an n by n by n Rubik's Cube, each side has area n squared. So total area is, surface area is 6n squared. So there's roughly theta n squared little cubies here. So what do you think the right asymptotics is for n by n by n? No guesses? N cubed? Reasonable guess? But wrong. It's an upper bound. Why n cubed? Oh, you're guessing based on the numbers. Yeah, the numbers are misleading, unfortunately. It's the law of small numbers, I guess. Doesn't really look right. I know the answer. I know the answer because we just wrote a paper with the answer. This is a new result from this summer. But I'm curious. So to me, the obvious answer is n squared, because there's about n squared cubies. And it's not so hard to show. In a constant number of moves, you can solve a constant number of cubies. If you think about the general algorithms, like if you've ever looked up Professor's Cube and how to solve it, you're doing like 10 moves, and then you solve, maybe you swap 2 cubies, which you can use to solve a couple cubies in a constant number of moves. So n squared would be the standard answer if you're following standard algorithms, but it turns out you can do a little bit better. And the right answer is n squared divided by log n. I think it's cool. Hopefully you guys can appreciate that. Not a lot of people can appreciate n squared divided by log n, but here in algorithms, we're all about n squared over log n. So if you're interested, papers on my website, things called Algorithms for Solving Rubik's Cubes. There's a constant there. Current constant is not so good. Let's say it's in the millions. But hey, you got to start somewhere. There's the next open problem would be to improve that constant to something reasonable that maybe is close to 20, but we're far from that. Okay, let's talk about graph representation. Before we can talk about exploring a graph, we need to know what we're given as input. And there's basically one standard representation and a bunch of variations of it. And they're called adjacency lists. So the idea with an adjacency list is you have an array called ADJ for adjacency of size v. Each element in the array is a pointer to a linked list. And the idea is that this array is indexed by a vertex. So we're imagining a world where we can index arrays by vertices. So maybe you just label your vertices 0 through v minus 1. Then that's a regular array. Or if you want to get fancy, you can think of a vertex as an arbitrary hashable thing. And ADJ is actually a hash table. And that's how you probably do it in Python. Maybe your vertices are objects. And this is just hashing based on the address of the object. But we're not going to worry about that. We're just going to write ADJ of u. Assume that somehow you can get the linked list corresponding with that vertex. And the idea is, for every vertex, we just store its neighbors. Namely, the vertices you can reach by one step from u. So I'm going to define that a little more formally. ADJ of u is going to be the set of all vertices v, such that uv is an edge. Okay, so if you have a vertex, where are my graphs here? So if I have a vertex like b, ADJ of B is going to be both A and C, because in one step there are outgoing edges from B to A and B to C. So ADJ of B is AC. Write that. In that graph, I should have labeled the vertices something different. ADJ of A is going to be just C, because you can't get from with one step from A to B. The edge is in the wrong direction. Okay, and ADJ of C is B. Okay, I think that definition is pretty clear. For undirected graphs, you just put braces here, which means you store, I mean, it's the same thing. For here, ADJ of C is going to be A, B, and D, because you can get in one step from C to A, from C to B, from C to D. This, for pretty much every, at least for graph exploration problems, this is the representation you want, because you're at some vertex, you want to know where can I go next. And ADJ of that vertex tells you exactly where you can go next. So this is what you want. There's a lot of different ways to actually implement adjacency lists. I've talked about two of them. You could have the vertices labeled 0 to v minus 1, and then this is literally an array. And you have, I guess I should draw, in this picture, ADJ is an array. So you've got A, B, and C. Each one of them is a pointer to a linked list. This one's actually going to be A, C, and we're done. This one is, oh, sorry, that was B. B, who said it had to be alphabetical order? A is pointer to C, C is a pointer to B. Okay, that's explicitly how you might represent it. This might be a hash table instead of an array if you have weirder vertices. You can also do it in a more object-oriented fashion. You could, for every vertex v, you could make the vertices objects, and v dot neighbors could store what we're defining over there to be ADJ of v. Okay, this would be the more object-oriented way to do it. I've thought a lot about this, and I like this, and usually when I implement graphs, this is what I do. But it is actually, it's convenient to have this representation. There's a reason the textbook uses this representation, because if you've already got some vertices lying around and you want to have multiple graphs on those vertices, this lets you do that. So you can define multiple ADJ arrays, one for graph 1, one for graph 2, one for graph 3. They can all talk about the same vertices. Whereas here, a vertex can only sort of belong to one graph. It can only have one neighbor structure that says what happens. If you're only dealing with one graph, this is probably cleaner. But with multiple graphs, which will happen even in this class, adjacency lists are kind of the way to go. You can also do implicitly represented graphs. Which would be to say ADJ of u is a function. Or v dot neighbors is a method of the vertex class. Okay, meaning it's not just stored there explicitly. Whenever you need it, you call this function and it computes what you want. This is useful because it uses less space. You could say this uses 0 space, or maybe v space, for one for each vertex. Depends. Maybe you don't even need to explicitly represent all the vertices. You start with some vertex, and given a vertex, somehow you know how to compute, let's say in constant time or linear time or something, the neighbors of that vertex. And then from there, you can keep searching, keep computing neighbors until you find what you want. Maybe you don't have to build the whole graph. You just need to build enough of it till you find your answer, whatever answer you're searching for. You think of a situation where that might be the case? Where implicit representation would be a good idea? Yeah, Rubik's Cubes. You're really good. I never want to build this space. It has a bajillion states, a bajillion vertices. It would take forever. There's more configurations of this cube than there are particles in the known universe. Yeah, just computed that in my head. I have done this computation recently, and for 5 by 5 by 5, it's like 10 to the 40 states, or 10 to the, somewhere 10 to the 40, 10 to the 60. There's about 10 to the 80 particles in the known universe, 10 to the 83 or something. So this is probably, I don't know, 10 to the 200 or so. It's a lot. You never want to build that, but it's very easy to represent this state. Just store where all the cubies are. And it's very easy to see what are all the configurations you can reach in one move. Just try this move, try this move, try this move, put it back, then try the next move, and so on. So in time, for an n by n by n cube, in order n time, you can list all the order n next states, you can list all the order n neighbors, and so you could keep exploring, searching for your state. Now you don't want to explore too far for that cube, but at least you're not hosed just from the problem of representing the graph. So even for 2 by 2 by 2, it's useful to do this mostly to save space. You're not really saving time, but you'd like to not have to store all 264 million states because it's going to be several gigabytes, and it's annoying. Speaking of space, ignoring the implicit representation, how much space does this representation require? V plus E. This is going to be the bread and butter of our graph algorithms. Most of the things we're going to talk about achieve V plus E time. This is essentially optimal. It's linear in the size of your graph. You've got V vertices, E edges. Technically, in case you're curious, this is really the size of V plus the size of E. But in the textbook, and I guess in the world, we just omit those sizes of whenever they're in a theta notation or big O notation. So number of vertices plus number of edges. That's sort of the bare minimum you'd need if you want an explicit representation of the graph. And we achieve that because we've got V space just to store the vertices in an array. And then if you add up each of these as an edge, we have to be a little careful. In undirected graphs, each of these is a half edge. So there's actually 2 times E nodes over here, but it's theta E. So theta V plus E is the amount of space we need. And ideally, all our algorithms will run in this much time. That's what you need just to look at the graph. Okay. So let's do an actual algorithm. Just breadth first search. So to the simplest algorithm you can think of in graphs, I've already outlined it several times. You start at some node, you look at all the nodes you can get to from there, you look at all the nodes you can get to from there, keep going until you're done. So this is going to explore all of the vertices that are reachable from a node. The challenge, the one annoying thing about breadth first search and why this is not trivial, is that there can be some edges that go sort of backwards, like that, to some previous layer. Actually, that's not true, is it? This can't happen. You see why? Because if that edge existed, then from this node, you'd be able to get here. So in an undirected graph, that can't happen. In a directed graph, you could conceivably have a back edge like that. You have to realize, oh, that's a vertex I've already seen. I don't want to put it here, even though it's something I can reach from this node, because I've already been there. So you've got to worry about things like that. Yeah, that's, I guess, the main. the main thing to worry about. So our goal is to visit all the nodes, vertices reachable from a given node S. We want to achieve v plus u time. And the idea is to look at the nodes that are reachable first in 0 moves. 0 moves, that's S. Then in 1 move, well, that's everything you can reach from S in 1 step. That's adjacency of S. And then 2 moves, and 3 moves, and so on until we run out of graph. Okay, but we need to be careful to avoid duplicates. We want to avoid revisiting vertices for a couple of reasons. One is if we didn't, we would spend infinite time, because we'd just go there and come back and go there and come back. As long as there's at least one cycle, you're going to keep going around the cycle forever and ever if you don't try to avoid duplicates. All right, so let me write down some code for this algorithm. It's pretty straightforward, but so straightforward we can be completely explicit and write some code. There's a few different ways to implement this algorithm. I'll show you my favorite, but textbook has a different favorite. I'm going to write in pure Python, I believe. Almost done. think I got that right. So this is at the end of the while loop. And at that point, we should be done. We could do an actual example, maybe. I'm going to do it on a an undirected graph, but this algorithm works just as well on directed and undirected graphs. Okay, there's an undirected graph. We're given some start vertex S, and we're given the graph by being given the adjacency lists. So you could iterate over the vertices of that thing. Given a vertex, you can list all the edges you can reach in one step. And then the top of the algorithm is just some initialization. The basic structure, we have this thing called the frontier, which is what we just reached on the previous level. I think that's going to be level I minus 1. Just don't want to make an index error. So these are going to be all the things you can reach using exactly I minus 1 moves. And then next is going to be all the things you can reach in I moves. Okay, so to get started, what we know is S. S is what you can reach in 0 moves. So we set the level of S to be 0. That's the first line of the code. There's this other thing called the parent. We'll worry about that later. It's optional. Just it gives us some other fun structure. We set I to be 1 because we just finished level 0. Frontier of what you can reach in level 0 is just S itself. So we're going to put that on the list. That is level 0. I equals 1. So 1 minus 1 is 0. All good. And then we're going to iterate. And this is going to be looking at the end of the iteration is to increment I. So you could also call this a for loop, except we don't know when it's going to end. So it's easier to think of I incrementing each step, not knowing when we're going to stop. We're going to stop whenever we run out of nodes. So whenever frontier is a non-empty list. And the bulk of the work here is computing what the next level is. That's called next. It's going to be level I. We do some computation. Eventually we have what's on the next level, then we set frontier to next. So because that's our new level, we increment I, and that invariant of frontier being level I minus 1 is preserved right after here, and then we just keep going until we run out of nodes. How do we compute next? Well, we look at every node in the frontier, and we look at all the nodes you can reach from those nodes. So every node U in the frontier, and then we look at, so this means there's an edge from U to V. So the picture, we look at all the edges from all the frontier nodes where you can go. And then the key thing is we check for duplicates. We see, have we seen this node before? If we have, we would have set its level to be something. If we haven't seen it, it will not be in the level hash table, or the level dictionary. And so if it's not in there, we'll put it in there and add it to the next layer. So that's how you avoid duplicates. You set its level to make sure you will never visit it again. You add it to the next frontier. You iterate, you're done. Okay? This is one version of what you might call breadth first search, and it achieves this goal, visiting all the nodes reachable from S in linear time. Let's see how it works on a real example. So first frontier is this thing. Frontier just has the node S, so we just look at S and we look at all the edges from S. We get A and X, so those get added to the next frontier. maybe before I go too far, let me switch colors. Multimedia here. All right, so here's level 1. All of these guys have, we're going to set their level to 1. They can be reached in 1 step. That's pretty clear. So now frontier is A and X. We go to that's what next becomes, and frontier becomes next. And so we look at all the edges from A. That's going to be S and Z. S, we've already looked at it. It already has a level set, so we ignore that. So we look at Z. Z does not have a level indicated here. So we're going to
Let me see if I can list this off. This is up for search though. So starts as an array, all zeros.
set it to
Okay, this guy's just cheating though. But he got his bachelor's at 14, and you got a PhD by the time he's 20. gotta use the restroom. fun with this. Learning material. But let's see if I can do a leetcode daily. And then I might just put some Overwatch or something. Okay. Oh. Okay. This one has high acceptance for daily. Minimum add to make parentheses valid. So let's see. So parentheses string is valid if and only if is the empty string. It can be written as a b, where a and b are valid strings, or it can be written as a, where a is a valid string. You're given a parentheses string s. In one move, you can insert a parentheses in any position of the string. Okay. This doesn't seem too hard. So you would take, let me try to use this counter thing. Python counter. So can I do Dania, is it capital? Yeah. We'll do it. Okay. We'll do left equals s dot counter of, and what would I put in here? Hold on, let me just watch YouTube video real quick on how to do this. I fucking suck at reading documentation. Bro, what am I watching?
What's going on, guys? Welcome back. In today's video, we're going to talk about something in Python that is going to be mainly interesting for beginners becoming more intermediate in the Python language, and this is the counter class. Now, the counter class is something that can replace dictionaries because a lot of beginners use dictionaries for counting, and I do so myself even a couple of times when I forget about the existence of counters. And today's video, I want to show you how counters work and why you should use them instead of dictionaries for counting. So first of all, in order to use counters, we need to import them, and for that we type from collections import counter. Now, this is part of the core Python stack. You don't need to install anything. We're also going to make use of random so that we can generate some random data. So import random is useful, and let's talk about basics.
From collections import counters. I need to do that. on here. Perhaps. So from collections import counter. I don't know if I need to do that, but we'll do it anyway.
Now, let's say you have a list of possible objects. We're going to call this object list, and you know that there are objects with a label A, with a label B, with a label C, with a label D, and with a label E, for example. You know these object types exist, and then you have an API, for example. You want to have the next object, and the next object, and you don't know what it's going to give you, but you want to count it. So you want to count what kind of objects it gives you over time. So what you can do is you can say, for example, for just counter in range 100, we're going to get a couple of random values. So we can say print random choice object list. Now in reality, of course, those are not random. Those are going to be some values provided by an API. You can see we get them, we get 100 of them, and we want to know, okay, how often did we get an A, how often did we get a B, and so on. We don't want to necessarily store them, we just want to have the counts. So what we can do is we can use a dictionary to do that. We can say dct equals empty dictionary, and then what we do is we say essentially, okay, we would have to initialize first of all for all the objects. So to start with 0, we would have to say for object in object list, we would have to say the dictionary entry for that object starts with 0, so we initialize, and then every time we say dictionary random dot choice of the object list plus equals 1. Or maybe to make it a little bit easier to read, we get wherever we get. So received object is wherever we get from the randomness or from the API. So random choice object list. And for this, we want to have an entry in a dictionary that is increased by 1 every time we encounter one. And in the end, we're going to have the occurrences. So we can say print dict. And then we see, okay, A was sent 21 times, B 19 times, C 21 times, and so on. So this works, but you can see it's kind of tedious. You need to initialize and all that. With a counter, this is way easier. With a counter, what you do is you say counter equals counter, like that. And you don't need to initialize anything. You can just skip that part, and you can just do it like that. So you can omit the initialization. Like that. So this works. This does not work with a dictionary. So if I change this again to a dictionary, this will not work because it doesn't know the key B in this case.
So how do you do it? He did
It doesn't work. We need to initialize it or we use a counter. But this is not the only thing that a counter can do, which is better than a dictionary. Also, one thing that I want to mention here that I cannot show you here today because I'm using Python 3.9. From Python 3.10 onwards, we can use counter.total to get the sum. So we can just type print counter.total, and this will give us the sum of all the individual counts. But as of right now in Python 3.9, it doesn't work yet, or it doesn't work in Python 3.9. It works in Python 3.10. And besides that, what we can do now is we can go ahead now and instead of getting them from an API, let's say we
so can we just do
have a collection. Let's say we have a list of occurrences. We're going to call this occurrences, and this is going to be just random.choices, and we're going to choose from the object list, and k is going to be 100. So we're going to choose 100 objects, and this is going to give us a random list. Like that. So we don't get them step by step. We have a list, and now we want to use a dictionary or a counter to count from that list the occurrences of the individual object types. So what we can do in a dictionary is we can again say dictionary is going to be an empty dictionary. We then say for object in object list. We want to initialize it again with 0. And then we can basically say, okay, again, count, basically what we did before. Now, what we can do with a counter here is even better than what we did before. We can just go ahead and say counter equals counter, and we can pass the occurrences, and we can print the counter object here.
okay. Can I just do this? Can I do the counter this. This be acceptable? Okay, so we'll do left is equal to this, and then we'll do right is equal to this. And we'll just return return the max of left, right minus the min of left, right, and then this should work. We can just submit that. Oof. Okay, now I see why this is a medium and not an easy. Okay. Okay. So I see what the issue is. It's I guess you have to close everything. You would need 1, 2, 3, 2 closing ones, and I'm just gonna look at the freaking editorial. This guy in 6 languages? Oh, it's 6. Where's the Python solution? Okay, so for this guy has comments and shit, so this is good. I'll have to. I can do this one probably. Then just do it again. But I don't want to be counted. Just chart. Sorry. How would you do this one? Um, probably just like a large. So. I'll go back. I can do this for the for loop easy. I don't know. For Wow, I don't know how to get past that. No, I think I know how actually. I just combine these two together. Boom. It's pretty clever.
Hey everyone, today we are going to
Yeah. And before we end the night, I want to learn terms algorithm.
Notice that B has been added to the video will show you the correct way to run Prim's algorithm on a graph. Prim's algorithm results in a minimum spanning tree, a minimum weight connected graph with no cycles. Let's run Prim's algorithm on this graph. To start, create an empty list called visited. We will use this list to keep track of nodes that we have touched. The next step is to pick an arbitrary node. We will start the algorithm from this node. Let's start with A in our graph. First, add A to the visited list. Next, examine all vertices reachable from A. They are shown in the graph with blue edges. Prim's is a greedy algorithm, so we're going to choose the smallest edge that connects to an unvisited node, in this case, A to B. The red nodes are the start of our minimum spanning tree. Notice that B has been added to the visited list. We now look at all nodes reachable from A and B. 3 edges all have a weight of 3. Pick one of these. I've chosen to add AC. Continue in this manner, each time picking the smallest edge that connects to an unvisited node. Notice at this point the edge BE with a weight of 3 is the smallest edge, but both vertices are already in the MST, so we do not pick it. Instead, we will choose to add F to the MST. The only unvisited node remaining is G, so we add this to the minimum spanning tree. All the nodes are now connected in a tree. Note that if edge weights are distinct, this minimum spanning tree will be unique. You can add the edge weights to get the minimum spanning tree's total edge weight. The time complexity depends on the data structures you use in your algorithm. The algorithm, shown here, is fairly easy to implement. And that's it. I hope this video gave you a good understanding of Prim. Today I'm going to teach you how to run Kruskal's algorithm on a connected graph with weighted edges. Kruskal's algorithm results in a minimum spanning tree. Let's run the algorithm on this graph. To start, pick the smallest edge. In this case, the smallest edge is between CE with an edge weight of 1. We repeatedly look for the smallest edges that don't create a cycle. In this case, edge AB with a weight of 2 is the next edge chosen. You can see that we have 2 trees forming, however they are not yet connected. Let's keep looking for the smallest edge in the edge list. Notice there are 3 edges with a weight of 3. You can choose any one of these edges. I have chosen to add edge AD to the minimum spanning tree. Continuing in the same manner, edge AC gets added to the MST. Notice the next smallest edge is BE with a weight of 3, but this edge connects 2 nodes that are already in the same tree, so it will not be chosen. Now we keep adding edges until all nodes are in the same tree. In this case, F is added with a weight of 7. Finally, G is added to the MST and all nodes are now in the same tree. We have our minimum spanning tree. This algorithm's speed is limited by sorting the edges. We can use merge sort to do this in time of E log E. Here is the pseudocode for Kruskal's algorithm. If you need additional help, see the list of sources below.
there's that done. And I think I'm gonna call it there for studying. I'm just gonna chill out now. Some Overwatch or something. Alright. And maybe in between queues. Okay, this is not my IP. Ooh. So let's open up some Kovacs, get some warmed up. I said that wrong. I was like playing on a podcast, otherwise I started thinking about random shit. Okay, let's see. Also, this is no moist critical video, bro. I don't know.
I imagine most of you were living your life in ignorant bliss, not even knowing there was a new Hellboy movie coming out. About 2 months ago, they released a trailer for Hellboy the Crooked Man.
I haven't seen Hellboy once, so maybe I want to watch that.
I like Nintendo games. I don't like Nintendo as a company. I've said this for 6 years now.
Fuck.
Nintendo constantly makes decisions that are actively just hurting the biggest fans of their property. It seems like they're just hell-bent on ruining people's passion for their properties. They're just on this warpath against fun itself. It's like when SpongeBob had to teach Plankton what fun is. That's what the community constantly does for Nintendo, only for them to just shout "bah humbug" and then send you a cease and desist, or just outright slap you down. Or if you're a YouTuber, issue you a strike. Oftentimes, Nintendo is evil for the sake of it.
Fix my
Like, I'm
posture.
talking mustache twirlingly sinister. Like, the Nintendo Corporation is a villain that Mario would have seeked to slay in one of his games. Like, I remember a case like 4 years ago where Nintendo banned a handful of streamers for playing Hyrule Warriors Age of Calamity early. Except they weren't playing it early. Nintendo just forgot that time zones exist, so they banned streamers who were playing the official release of Hyrule Warriors because they forgot. That's how out of touch and archaic Nintendo is, and how willing they are to just bend someone over and spank their cheeks raw, even when there's no real reason to do so. This is something Nintendo has done for years now with like Smash Brothers, which I've talked about endlessly, but they get up extra early in the morning just to hate. Like, they try and just ruin fun. Nintendo would send assassins to Santa Claus's workshop if they found out that one of the elves made an unlicensed
Wow,
Yoshi plush.
one away from my high
I know
score.
I'm getting a little lost in the sauce here, but I just get very passionate when I talk about how menacing Nintendo is for no reason. So the reason why I'm talking about them today is because they've just dealt a massive blow to emulation. Nintendo deserves more shit than a porta potty for this, and I really hope they get huge backlash for it, because I think this is just completely unacceptable. It started 2 days ago with a channel called Retro Game Corps announcing that they had received strikes for content that had a Nintendo game running on an emulator. The channel owner explains that they are considering a counterclaim under fair use as it was educational and transformative and had no effect on the market. It was a demonstration of a console no longer for sale. Even the Wii U eShop is closed, so the company itself has no means of earning revenue from Wii U sales. So this is one of the core components and what makes emulation so important. There are games that aren't being sold anymore and cannot be accessed outside of emulating them. It's fucking ridiculous. It is an incredibly important tool for preservation. But the only thing Nintendo's interested in preserving is that chip on their shoulder they have against any kind of internet content.
New high score.
Games. So they once again overstep and issue strikes for this, which is something Nintendo has done since the dawn of YouTube itself. There was a time period where you couldn't actually have a YouTube video that had a Nintendo game in it because Nintendo would have your account banned. They fucking hate it for some reason. They try and protect their copyright with an iron fist. And I know there's always people that have Nintendo's cock in their mouth trying to make arguments on their behalf, doing free PR for them, fighting their battles, saying things like, oh yeah, but people will download games that they don't have on emulators and that hurts Nintendo. Load of baloney. That's dirty barnacles, especially in cases like this. There is no one getting hurt by emulating games that are not accessible through a
I think I'm good.
There is tons of games like that.
Not much
Emulation
time
is
anyway.
extraordinarily important, and Nintendo does everything it can to ruin it. And in doing so, they even try and ruin other people's lives in the process.
Okay, screw that. And then I just remembered something I wanted to look up on much. Let's go to. I wanted to look up what a priority queue is. I know what a regular queue is. It's just this one.
Hey, everybody.
Let's go, guys. Season ends in 5 days, bro. That sucks.
It's your bro, hope you're doing well, and in this video we're going to discuss priority queues in computer science. So sit back, relax, and enjoy the show. Hey.
Wait. What's my competitive progress? Look at my content. Oh, it's not great. I'm almost Masters 1 on support.
Hey, what's going on, everybody? So, priority queues. A priority queue is a FIFO data structure, first in, first out. However, a major difference with priority queues is that before we start polling and serving elements, we put them in some sort of order. Higher priority elements are served first, before elements with lower priority. So here's an example. Let's say that we have some student GPAs, and we'll place them all within a queue and then a priority queue and take a look at the differences. So let's create a queue. The data type is queue, and we are going to insert some doubles, some GPAs. I'll name this queue equals new. Now queues are actually interfaces and we can't implement them directly, so we need to use a class that utilizes the queue interface. One that I know of is a linked list. Then finish instantiating it. Now to add data to a queue, we use the offer method. Queue.offer, and then pass in a GPA. Let's make sure that these are not in order. How about a 3.0? Then the next student has a
Q.offer? Since when is that a thing?
2.5. Then a 4.0, 1.5, and 2.0. Okay, now let's
to talk about multi-dimensional arrays in Java. Let's take a look at this example. Here we have created a
I mean, this one's cool and all, but like it's probably cost a lot of money. How much is this? Let me do this off screen. It's like 40 bucks. Don't think that's worth it. Especially when it's probably free. The all information that's free.
Now arriving at the Shambhali Monastery.
Voice chat may be recorded to investigate and verify reports of disruptive behavior.
One small step at a time.
Five, 4, 3, 2, 1. Attack commencing.
Let's take off!
Escort
Enemy here. Destroy that parrot. Soldier 76 reporting for duty. Enemy turret destroyed.
Light speed!
Enemy turret sighted.
No, I must not think like that.
Enemy turret destroyed.
Push the payload. I will fix that.
Hello. No time for R&R. Push that payload.
Come to me for healing. Through here.
Send this shotgun again. We need to move that payload.
Watch Queen ult.
Time for the reckoning.
Light speed.
Do you only play Zen? I see a girl.
No.
My ultimate is almost ready.
They have core, rally.
I'm with you, Genji.
Enemy here. I will assist. 30 seconds. Over there.
Okay, they still have Molten Core and Rally. Let's
Where? Okay, never mind. All good.
Time for the reckoning.
Oh, okay. That works.
Queen won. Queen really won.
Now we're in orbit.
I fucked up.
My ultimate is charging.
Alright, they have Ana now. They're gonna have just Genoa, I think soon.
That's not bad.
You can't beat me.
Score 3-0. Switching sides. Prepare your defenses. Select your hero.
We must take one small step at a time.
We will be the lightning that rides the storm.
The snow here is quite mild compared to the ice caps back home.
Just another day in the office.
Five, 4, 3, 2, 1. Attackers incoming. Stop the payload.
Enemy here!
Enemy turret destroyed.
We're inbound! Maximum velocity! Apologies, you were in my flight path. Hi. Ring deployed. Orbital ray is not ready yet. My ultimate is almost ready. My ultimate is almost ready.
Watch wall, near wall.
There's a monkey behind. Oh, he's on me. Monkey low on me.
Oh,
He's
that's
after one.
so bad. Ash one, Ash really one.
Green on TP.
Okay, your Juno's on point. Okay, watch Primal here and Male. We should... Curie won, Curie really won. No Suzu, no TP. Oh.
Damn.
Let the Kitsune guide you.
The enemy outnumbers us.
Okay, I just give that up. They're gonna have what, like Primal, Male, Nano?
They don't have Male, they used it.
Oh, they do. Okay, so Primal and both support ults.
He was Curie.
Oh, okay, so Primal and Nano.
Maximum velocity. Enemy over here.
They use Nano.
Oh, I fucked up. I forgot to cancel my boosters. I'm good, thank you though. My bad.
Okay, they have Primal. Male, Bob.
Oh, Fury's the one on the mini.
Monkey really won. So won. Holy shit. Curious on. Oh, what's on there? Oh, killed their monkey there.
Score 3-3.
One small step at a time.
5, 4, 3, 2, 1. Attackers incoming.
Spotted. Enemy over here.
The pain.
Doing that.
The dragon becomes me.
Taking heavy fire.
Score 3-3. Switching sides.
One small step at a time.
Let us proceed with haste.
If you knew what Blackwatch was up to, why didn't you stop them?
My vision was clouded by anger.
And now the world pays for your actions.
In that, we are the same.
Five, 4, 3, 2, 1. Attack commencing. 60 seconds.
pushing up here.
Juno one. I got Ash.
Where no fitting? Nice. Nice job.
GGS. Match. GG.
Play of the game.
Time for the reckoning!
Let me use the restroom real quick. Got myself a granola bar here. Let's try to get this done. So.
Welcome to Esperanza.
Team. I think they have a Genji OTP. Yes.
One small step at a time.
Don't be afraid to ask for help out there.
What?
Oh, do you want Juno? You can have Juno.
Another day, another battlefield.
3, 2, 1.
Breaking me down just builds me up. Enemy here. Shields under fire.
We are pushing ahead.
Tracing shield. Helping you recover.
You're back into it.
The enemy took. I have a new plan this time.
They are making progress! Stop them!
I'll cover you.
Affirmative. Enemies in the lead. Cry.
Get it. Moving forward. We've got to stop them.
We are providing escort. I know. An enemy comes.
Enemy over here.
I don't think we have heals. Let's try.
Not right now.
Your team is close
We are
to
close to
taking the
achieving
lead.
the lead. Making progress. Let's stay with him.
Hyperring deployed.
Over there.
Nice, dude.
Push car for me.
Teammate.
I'm baiting ready.
I see one.
Ah, nice. Chris here. Nice shot. They should have JQ ult. I think we need to stun it.
The lead is ours.
Can we just kite Juno and re-engage with our Juno? So I'll try to save slow.
Get healed here.
Time for the reckoning!
Welcome to orbit!
That's not gonna
Make sure you die on point. So you don't get- nice.
That wasn't the plan.
Forward spawning loss.
slowed their backline.
Oh, this Genji just sucked. My bad.
What do you have? Spam their backline, spam their backline. Juno half HP.
Hostiles approach.
Almost have ult.
Don't let them get away with this. We can't let them take the lead. We're outnumbered. Careful.
Okay, Genji has Blade next fight.
I don't know what to do to help you guys like not die.
I mean, that's my bad. No, I don't know.
Going, sorry, yeah.
For you. I'm under fire. Over there. We can't let them take the lead. Oh no, we've lost the lead. Hello.
Your team has lost the lead.
They're moving the barricade. Enemy over here.
Time for the reckoning!
Throw it to me. Trust in the process.
Walk up with me though.
I see one. Blocking satellite vector.
I can believe it. You guys keep dying.
I mean, they had ults. We all swapped characters, so we didn't have anything.
Welcome to orbit. They're coming. We'll get you where you need to go. Let me help you guys. Come here, I'll heal you up. We need to get that robot back. We need to stop them. Allah till
Fire at will! Time for the reckoning!
Approaching the final
Call me good
I
at
don't
game
know,
me
bro.
play JQ Bridge Juno. Skill. Apes.
That was tough.
Dogged. Duo. Vet.
Vax real quick.
Yeah, we can do that.
What rank are you?
Masters 2. Where you at?
Masters 5.
Okay. Are we within range? Or does it say YQ?
We're in range. I was just
Okay.
curious.
Okay.
Let me hit the Vax though, because I just been playing Silent Hill for. I haven't been on watch in I don't know, 2 or 3 days.
Yeah, last time I was on watch, I played with you. So I think we're in the.
It's been a while for me. We just
Fight. Select your hero.
It's time to save the realm. One small step at a time.
I've been kind of turned off from wanting to play this game.
Really? Wow.
I just get too frustrated. Also, I've been wanting to play Silent Hill.
That's fair. End of the season. I don't know if you saw it. It's 5 days left.
I know. I gotta grind a bit more before the season ends. Have you been winning?
I played 2 games. Won one and lost one. So the one I lost was a consolation. So I don't know. I'm not so upset.
You gotta get an ult account, man.
Yeah. Well, maybe. I don't.
That's not really. But kind of nice to have one sometimes.
It would be nice. I don't have. I guess. Yeah, I guess an alt would be nice. Usually, if I want alt, I just play another role though. Sometimes I don't want it.
Yeah.
Tower in orbit. I see a sniper. Like a solar harvest after a dust storm. Return to Stardust. I'm here.
Okay, I guess I'm probably ready to go.
Okay.
Just a tank player.
Oh, that's not very fun.
How many Overwatch coins do you have?
Like the old ones?
The yellow one.
The yellow, 1400.
Same.
Oh,
I'm
really?
tempted to buy. If you go to the shop and scroll all the way down.
Do
we have the same shop? Do you see the Ramattra skin, Kabuki?
Oh yeah, I see that one.
I'm kind of tempted to buy that skin. I don't know if the coins are put towards something else.
Oh no, I don't know if that. That sounds the same. No, I don't have it. I just tried it out. Just the trial button.
I mean, I feel like Ram skins, they're kind of shit.
Yeah, they are. They're pretty bad.
People think he's gonna get a mythic next season, though. I don't know if it's true or not.
He had one. Wait. Let me see. Oh.
A mythic?
I think so. One of the battle passes I think had it. Let me see though.
Prepare for battle.
Oh, I can't see actually.
Select your hero.
I'm not saying.
Damn, you didn't get Max Level Virgin name?
No, I haven't yet. I don't think I can anymore.
I think you're locked out, man. To
Frick.
break it to you.
Damn.
I forgot. What did I play here and it worked well? Low-key, I should play Queen, but I think my Queen is just, I don't know, not up to par.
Terran speaks so many different languages.
Was it Monkey or someone that could get on that high ground? Who is it?
Oh shit, should I play with my controller? My controller is turned on.
Probably not.
Look at this, look at this.
Where outcomes are uncertain, but I am
Dang.
going to have a great
Looks like you're gonna log out.
I don't want to hit my controller in accident. Queen, I don't know, maybe next season I'll play Queen.
Next season? She's gonna get probably nerfed next season.
I hope she was nerfed, she's fucking annoying. I don't know. I don't know if it's worth learning a new hero. It probably isn't. You don't want your hero pool to be too big. Orisa, bro, really? Orisa's super meta as well.
Yeah. What is all this space? Are they down one or something?
I don't know.
Or someone, or someone.
Orisa, nice. I can go down.
I come on.
Oh gosh.
The rock
burning.
Beating.
Genji one.
Oh god.
Oh shit.
Okay.
Family.
Worth it. The fuck did we were just saying?
I have no idea.
What
Some
language does he speak?
Thai? He's from Thailand.
Super
So,
high for the last one.
Thai? Is it Thai or is it Mandarin? I don't know.
Did he have ults? It's probably gone.
Oh gosh.
There's on a goal.
I think they might have it.
Lucian one.
I did not.
Wait, Lucian one.
Okay, I'm gonna go. I might have fire
That's tough.
Oh my god, I got it.
Yeah, that's fine. Don't use any more.
Oh gosh.
There's no stopping me.
Okay, Weaver's kind of good on this map. The pedal set you can use.
Yeah. But if you use it correctly, yeah.
They use mana, gosh.
Yeah, they're probably everything else.
Maybe straight, so
I can go left.
Oh.
He's gonna hold me. Jump in.
Where's the one? Really one?
The Orisa is garbage, bro. They're all left here.
Cast one.
I can't get down there. Cast me?
Genji one, really one. Cast one. Oh shit.
Oh my god. Of course he gets fucking beat. I think we can turn this. Do you want to use it?
Yeah, I can. My bad. Do not touch.
I don't want.
All one. Cast one.
Stick one.
Lucio weak.
Lucio.
Oh, Genji point.
Yeah, good job.
Genji's so weak. Oh, but was not needed. Right.
Just play
That
next.
sucks.
Ah, that's close. Holy crap, I'm freaking bodying these kids. Hold up.
Oh my god, that projectile side. Interesting.
Let's give it to him.
So powerful.
Damn,
God
what the
damn.
fuck?
Life protects life.
What's up? Can't get it out. So thinking on it.
Yeah, so she's back there.
What's up, fuck?
I don't want.
Listen one.
Get the one on my point.
Yeah, what's up, I'm just
Oh, you don't know what's going on anymore. God damn.
Frick, bro.
So this is the fucking dumbest shit ever. What? You can still fight it.
Yeah, I'm just have orbit.
Let's open it overall. I'm right now.
I don't want.
I don't know. Back my god. Yeah. I'm feeling bad there too.
Yeah, that's fine.
That's why.
We're in a better spot. Hey, watch Nano soon.
Oh my god, you actually have this.
Oh my god, this is wrong. Go for it. I'm not there.
Cast one, get you one down and all one. Cast one is on.
That's what it would be, like up here?
Probably, that's probably a good spot.
Not really, I have to be like back here.
Yeah, I should probably be somewhere else.
There's the left.
There's no gold.
No.
This is just a.
Oh my god. Poop.
You see one.
Ana checking in.
Splashdown.
Let's increase our pace. Orbital ray is nearly ready. Orbital ray is ready to fire.
Okay, one orbital. This is not fun. We should push.
We can't go up there. Nothing.
No, bro.
That's one.
Cast someone.
Holy shit, I'm fighting demons. What's on?
I'm here. It's with.
Yeah.
Getting out.
There's someone. Get you one.
Oh, that's right.
Just one.
Yeah, that's. Oh crap.
Oh, okay.
Get you one, get you one, get you one.
I don't go in the back.
This is behind us.
Go faster.
Yeah, that's one.
Boom.
Oh my god, oh my god, oh my god.
Nice.
Oh my god, oh my god, oh my god.
Groove.
GG.
Match. GG.
Yeah, this game sometimes, man.
For real, bro.
Play of the game.
What? I love BTGG.
I don't know what that means.
I don't know either.
DPS gap.
Yeah, it's like on the issue, it's whatever.
Ew, you just got fucked.
That's funny.
Go. Positive.
Let's display the elements of our queue. One easy way in which we can do that is to use a while loop.
You've been doing lots of studying.
Oh yeah, all day today. And the
Yeah, I see your stream. It's just been like leetcode and stuff. Or,
yeah, dude.
Watching algorithm videos, I think.
Yeah, that sounds about right. Let's see. I have a midterm, like a midterm on Tuesday, and it's like the class is like just 2 tests. It's like a midterm and a final, and that's like basically your whole grade. So, it's the good stuff. It's one of those
when are exams?
It was last week. For most, like all my midterms are last week, except for this one, because this class only has 2 exams, so it's just like, the middle. But what have you been up to today besides just playing Hollow Knight and work? Were you at home today for work, or were you on site?
No, I was just at work all day.
Dang.
And then yeah, just started playing Silent Hill when I came home.
Nice. Did you see that Amazon's like not doing any more remote work? Like they're bringing everyone in.
Yeah, people were saying Amazon wanted people to leave or something. Like people are staying too long, or I don't know what that means, but I don't know, something like that. I don't really get it. I don't know.
I don't really get it either.
Yeah, man. Don't miss having to take exams.
Yeah, dude, they suck. It's not the worst thing in the whole world. I think it's still better than like manual labor. You know what I mean? So hitting the oil rigs.
Labor?
Like yeah, hitting the oil rigs and shit.
No, I'm not doing that shit.
Yeah, bro.
I'm not built for that.
I'm not either, bro. Rockin'. Oh, how is relocating to Texas once you like got your job? Did you have family in Texas?
No, I just kind of moved there. My family helped me move here, but I didn't really have shit. You know, when you're in college, you don't really have shit.
Yeah.
But yeah, we drove here from Chicago with whatever stuff I had. And moving's not fun, but it was fun to go somewhere new, and you know, to be here is exciting, and finding an apartment, all that.
Did you move there because you got a job, or did you get the job because you moved there? Okay.
No, I got the job here, and so that's why I moved here.
I see.
But yeah, I don't know. I mean, I like being here, but I don't know if I'll stay here.
Yeah, I mean that sounds pretty. If all your family is like over in Chicago, sounds pretty.
Yeah, and that part of it sucks, but I don't really feel like I need to. I don't know if I want to like live in the Midwest again.
I see. That's fair. Probably after being in Texas, then you probably never want to go back to the.
Yeah,
Yeah.
yeah, true.
Got a good cigar, big iron.
Jared, did the company pay for your relocation, or was that all on you?
Maybe something to drink.
Wait, what did you say?
Did the company give you like a relocation package where like they paid for it? Or did
Yeah, I
just...
think it wasn't anything crazy, but there was like that a bonus and that sort of thing.
Okay, very cool.
Behind you! Ah! Behind you! Ah! Behind you! Ah! Behind you!
Target's dancing.
Behind you!
Yeah,
But
bro.
his skin is ugly as fuck.
Yeah.
The soldier skin, I mean.
Yeah, it's. Okay, hold on.
Oh god. Oh, that's Ram. I thought that was a Arista shooting.
Okay, Anna.
Give her on, babe. Look at hell of space. What this guy out of here? What a fucking throw. Easy in.
Very free. And our BAP's dancing again, bro. Look. Okay.
Get it. How about this low ground idea? It's a bit stupid. That Ram has to play low ground. Useful. Damn. No, this Ram sucks. He just kills fucking nothing. Get the hell down. Ram, come down.
Okay, I'm low ground.
That's the one that's flag, dude. Kill him.
Cass is still one.
Oh, you're gonna die, careful. Oh, well, not.
Yeah.
I thought the Hanzo was fucking right at you. But...
Oh.
Oh, you should press Q, I think.
Oh, the debate.
Oh, shit.
He still won. Oh, wow.
Oh my god, he died? No, my fucking block is dead.
Cast one, cast one.
Cast. No cooldown.
Oh.
I did my job. I don't know. I did what I could.
Yeah. We did too. Maybe we should have gone for support first. Fuck Cass. He was one. Wow.
Yeah, you just won. Yeah.
Let's get the payload back on track.
What the fuck? He beat the fuck out of my fucking rock. I was ignoring him. Not gonna go beat it.
Crap. Yeah, we use lamp.
Yeah, that's actually huge. I know, for sure now. I mean, is that just a goaded ult or what?
Yeah, it was just goaded. That was nice.
I missed a rock right after I said that. Oh my god, I moved into the fucking staircase.
Goodness.
They have Sombra now?
Yeah.
Now, what is this ball theory?
Ball theory? Ah, dude. What shit.
Getting duped by fucking ball theory. And everything. Fucking push.
Oh, wait. Fuck, those are good mines. Okay. Yeah. All one. Good one.
Dominating too much.
Nice. What a great push.
Honestly, what a great push.
Score.
I seen a video which is like, it feels good to be a winner. And I'll just let you know. I still watch it.
Okay. Have you seen I don't know how much you keep up with it, but have you seen the fucking the KSI song? Shit.
Yeah.
Fucking everyone clowning on that shit. Oh my god.
I see this shit on I see all like the drama always on Twitter. Look at voice chat.
Yeah, let's see this. Yo, what up, Underhood?
What up?
Young Joe.
It feels good to be a winner.
Feels good to be a gangster.
How goes it?
Just playing some watch.
I don't know if Diamond 1 is high enough to queue with you Masters 5.
Maybe.
Or you could try. We could try it. I don't know.
I climbed from fucking like Plat 5 to Diamond 1, so I'll take it.
I remember this like a couple weeks ago. You were like, "Is Plat high enough to queue with you guys?" And then it wasn't.
Hell no. Can't like play support with any like the other stack because it's too high.
Oh.
Like
that stack is a bit of a different vibe. You know what I mean?
You know, it's usually just like the stack usually ends up being like Roman, Jared, late.
Oh my god, I actually get fucked by that.
But now I just have to play tank because I think I don't play support.
Tank is not what it used to be.
I fucking hate it.
Wait, I just kind of dick dug it now.
Yeah.
I'm being real about it.
Oh crap.
Alright, I'm overextending mine. If I hit that rock, would have been crazy, but... What? I hit her in a what? It didn't stun her in res. That's not fair. My rock
Yeah.
hit her, but it didn't stun her.
Oh, I know what you mean.
And like point blank.
Report the tank.
What? Yeah, their tank,
Their tank has
oh
9 deaths already?
Bro, that
Oh.
guy is so garbage.
Oh my god, I didn't realize we already attacked, bro. I felt like we were still on defense. Or is it? Okay.
Oh, you thought it was those 9 deaths?
Yeah, I was like, holy fuck.
That would be a crazy stat. But they did better.
Someone's coming to the train, maybe? I don't know.
It might be Ryan, but I don't know if he's that crazy.
He don't see the 2-5. Duo sure.
I mean, there's typing in chat.
Gap by Sid. This map is a
Like,
tank.
he's typing.
I don't know.
I'm not
Oh, our soldier died.
Oh no, we can't throw this. Wait, that hit me? Oh no, it might be throw over here.
Just look at him.
Look at this Reinhardt, bro. What is that? Can I stand here? Wait, is that Loki kind of attack or what?
Oh shit. Hold on, let me get up there.
Yeah, get in here, get in here.
I'm gonna hit the bat right quick. Okay.
Oh shit. Oh no, it's taking my damage actually.
Yeah. Okay.
Like, Ryan definitely can't shatter us from here now.
Oh, that fair is one. I'm gonna go for her.
Yeah, let me just go for her. You're
I got her.
Oh shit, you got this.
Yeah, bro.
Look what they're doing, bro. Look.
I mean, this team is just unfortunate. They have a Rhine player and a Mercy player who plays Life
The thing
Weaver.
about this game is that's gonna be us like next game.
Yeah,
That's how this Overwatch works.
GG, I guess. A voice.
Who was their Mercy? What was that? The person's name? Sec?
Unistal Juno.
Oh my god, were they in the duo?
Players to
Oh no, they
your group
weren't.
While in competitive play. It feels good to be a winner. Unable to invite players to your group while in competitive play. Brain dead. It feels good to be a gangster. TV.
The voices, man. Voices told me to shoot there.
Like I understood the reference.
Yeah, he did. he did.
Wow.
I like it even at the T he.
Oh wait, let's see if we can get Underhood in here.
Let's see what's under that hood.
Show you. Yeah, if it's wide, it's fine. I'd be up for much longer anyways, but... Oh no, I can't.
Well, I only if I play DPS. What's one wide game? Alright. What do you lose, like 1 SR if you win? If you lose or some shit?
Good question, man. Good question. You're gonna lose like 30.
I'm trying to
Yes,
regrind
like
some
one.
watch since I might be the Overwatch coach at my high school.
Oh shit, that's so sick.
Really?
Yeah.
Damn, that's cool.
That's actually really cool.
They have a Valorant team too, but I've never fucking played Valorant, and they still want me to coach that, and I'm like,
You can coach it, you know, if you.
I don't know the
I'm sure
names of
those,
characters, bro.
I'm sure there's slightly more with like teach the team play and the game
Right.
sense. You just need someone with an outside perspective.
I think it's still the same thing, like you just use your cooldowns and like you don't I don't know actually. I don't know anything about it.
It's more like Counter-Strike. That's
I
a bit
played some
harder.
CS, but
It would probably be hard to coach Val because it's more like just running strats and stuff. And Overwatch, it's not really strats. It's more just like at the top level, it's more like a chess game.
Do Diva. I've only seen
Go
Diva.
Diva.
Like, I've just seen so much Diva.
Diva doesn't seem that good anymore. I mean, she's definitely not bad, but she's definitely not broken like she was. I want to get a watch. I don't really have any watches.
You want to watch? Let me see if I can find one.
Do you have any watches?
Nope, just the Overwatch.
True.
Oh my god, this shit's clean as fuck.
You're about to send me like a $30,000 watch.
Oh yeah. How do I? Hopefully this works. Oh, look in voice chat.
Yeah.
And I copied a space character. Hold on. Look at that.
Oh. Yo.
Look at how clean that is.
Holy.
Oh, the
That
Overwatch.
is sick. What is this website?
I don't know.
Wait, look at this.
Angie Quartz.
Look at
Oh my.
Oh.
That's
okay.
fire, bro.
Okay, now we're talking.
I think I should pull up to school wearing that.
Yeah.
I think my students would think I'm cool.
Yeah, that'd be like.
Like 10-pack chug
Yeah. That's pretty bad.
What is this website?
Guys, look what time is it, guys? Oh, let me just pull out my Overwatch.
The
Overwatch. That's crazy.
Do you guys have any Overwatch like merch? Like,
do we own any?
yeah.
I don't think
I still have my Dallas Fuel hat.
I have a like Overwatch League like jerseys, and I have that hat too.
That's pretty sick.
I got our lanyards from back in the day.
Oh no way! The Tesla lanyards.
Yeah.
Damn.
Somewhere here.
Damn.
I think it
that's
survived the
legendary.
move to Columbus. I have my Reinhardt Funko Pop that got destroyed over the summer.
How did it get destroyed?
I brought it out to summer camp as like we had to choose a totem that represented us for like kids when they came into the dining hall. They picked someone's totem and then you sat at that table. And I was like, fuck it, solid piece of plastic, Reinhardt, whatever, don't care. Somehow by the end of the summer they managed to like break off his leg, his arm, his
What
fucking.
the
And I
hell?
was like, holy shit, man. So he's a little busted, but he's fine. I can fix him.
What grade level do you teach?
I teach 9th grade
Ninth
freshman,
grade? Ah.
but I worked at a summer camp that had like 11 to 17-year-olds, so a lot of skibbity rizzlers.
Oh yeah. What subject do you teach?
I teach US history.
History? That's pretty chill.
Yeah, it's not bad.
How do your students do?
They're really bad right now.
They're really bad.
They're
History
just like
is hard.
just academic deficiencies or like I mean, students don't know. Like we were talking about Civil War Reconstruction, and I asked them to answer this question from the perspective of the North and the South. Should Confederate leaders be tried for treason or pardoned? And they didn't know what any of those words meant. They didn't know what treason meant. They didn't know what pardoned meant.
Oh damn! That's...
I had one kid ask me, so wait, which side were the Confederates? And I'm like, bro, you studied this in middle school. What do you mean?
Damn, that's pretty sad.
Not gonna cap, bro. I wouldn't know that.
The South.
I learned that.
North and South, bro. Come on. No, they're just really behind. You know, they're really reliant on AI, and
that's
I already had
very,
one person submit an
worrisome.
AI assignment, so that was fun.
How'd you know it was AI?
It's obvious. I assign everything we do handwritten everything in class. I think that I have them on their computers maybe for a total like 10 minutes for the hour and a half I have them. Otherwise, I print off all the worksheets. We do everything on paper by hand. And I don't assign homework because there's no guarantee that they will just cheat when they get home. But no, the student had handwritten this paper, but it was like, oh my god, it was like a college graduate level writing. And
Okay.
you're supposed to use documents that I provided and cite like direct quotes. They didn't do that. And when a ninth grader is talking about the effect that they were using like contemporary democratic governance and shit like that. And their last assignment, I asked like what divides Americans today, and they say their writing was like, Americans disagree on dumb things. They yell on social media. You know, like that was their level of writing. And then all of a sudden they submit this paper talking about the
Hey, they just turned up, man. They
yeah,
turned
they
up.
really did. I know. I asked them. I was like, "Did you use AI?" And they're like, "Yeah, I used ChatGPT." I was like, "Cool, case closed. Thank you."
Well, at least they're honest about it.
How'd you
Yeah.
punish them?
They had to redo the assignment.
Oh.
That's good. Like making them redo it, you know, is at least like, you know, you're caught. You admitted you're caught. You know.
Yeah, the school was supposed to give them detentions for AI usage, but they backpedaled and now are not doing any academic like consequences for AI usage outside of having to
weird.
redo the assignment.
Like, you
Because some
kinda
teachers
want
are
them to
allowed
be good at
to.
it.
We were able to choose our policy if we wanted to allow AI in our classroom, but only I think about 10% of the teachers allow AI. Because yeah, it's just breeding this mindset in the students that's really, really bad. Like they watch the TikToks of college kids using AI and cheating and like, oh, I don't need to take notes anymore. I can just have my phone record it and it will generate notes for me. And I'm like, that defeats the whole purpose because you're not going to go back and fucking read those.
Yeah.
Like you're not. If you really honestly think that you're going to record an hour and a half lecture in college and go back and listen to it or like look at your AI notes, you're just not. You're not going to do that.
It's like you would want people to get good at AI and use it for positive things, but when you're just learning how to do stuff for the first time, I don't know, it's
Yeah.
just like gonna replace learning.
I'm just trying to get like their ability to form an idea by themselves. That's a struggle. Like if I ask them a question, they will, and it's like an opinion or like using what you know, just come up with an answer, right?
Mm-hmm.
They always ask me, well, this isn't in the worksheet, this isn't in the text, and I'm like, no, it's not. It's in your brain, dude. Like think.
It's in your brain.
So it's just, you know, it is what it is. Also, damn, I haven't had a wide match in a while. This is a long queue.
Oh, I forgot we were in queue.
Dude,
Shit.
this is like my normal queues.
Really?
Really?
No. Sometimes in the mornings.
I'm about to say, I play like for a couple hours or like an hour in the evenings, and queue times are like 2 minutes tops. But I don't wide queue ever, so.
All my favorite streamers, you know, like pro players, have to sing queue for 20 plus minutes. It just like sucks. I'm not gonna watch their stream of them just like watching YouTube in queue.
Yeah.
You know?
That does suck. I don't know. Do you use ChatGPT to create your assignments?
No, I made I just, I mean, you can probably guess my thoughts on AI, but I
Yeah.
told the students, you don't use it, I don't use it, because I think it's cheap. That honestly, like, I don't like, well, one, like, a lot of AI, like, there's a possibility for it to hallucinate, so it's like, you can't just use it, like, and expect your lessons to be high quality. Like, it's gotten information wrong, like, it misinterpreted. We tested it in the social studies department, just misinterpreted the Federalist Papers, like what James Madison's argument was, and it was just wrong. Like it was straight up wrong. So our admin has allowed us to use AI for our planning, but we have to double check and fact check and like verify everything. But I don't use it. No, I don't use any AI because I tell the students, you don't use it, I don't use it.
Man, it sucks because I see the good in AI, but right now it's just being
I just think
used
it's in a
wrong.
bad spot. Yeah, I don't know. But I don't know. I went to college to learn how to like design meaningful lessons for students. I don't need a computer to do that for me.
Yeah.
Like I know what my students need and what's best for them, and I understand the content more when I create it myself. And also I don't have to worry about fact checking.
That's good.
I went to college to learn how to code, but I still use ChatGPT every day.
Same, bro. I use it to summarize my notes, I'll do everything with it, bro.
It does hallucinate stuff and does get shit wrong a lot. You know, you have to know enough about what you're working on to like when I ask it to solve some coding question, usually you can get like bits and pieces of what you need, but you have to be able to decipher what's wrong and what's right.
Yeah.
You ever heard of Cursor?
Yeah, Cursor looks pretty good.
Use Copilot or like just exclusively?
I just use ChatGPT. Imagine if you are using all those tools, you probably can get a lot done.
I think there was a paper released that, or like I read an article recently where like people don't get as much done because of tech debt.
Yeah. You mean from AI?
Yeah, from AI. Because something along the lines of that.
If you're just copy pasting stuff from ChatGPT, yeah, you're good. That just means that you're pasting stuff in that's incorrect. But that wouldn't be the case if it always was correct, which is, you know, what we're striving to achieve.
Mm-hmm. Do you have a favorite student in your class?
I don't have any favorite students.
Damn, they're all bad.
No, I mean that's just what I tell them all the time because they're like, "We're your favorite class, right? I'm your favorite student, right?" And I'm like, "I don't have any favorites."
But you do.
Like
as I
secretly.
explained to the students one time, I was like, I mean, earnestly, like obviously, I don't have any ill will towards any of my students. Like, right, I'm fucking getting paid barely anything to spend, you know, all of my life doing this. I'm not here to hate on any of you, but there are certain students who I respect their effort and their attentiveness more than others. And I think that's a fair thing to say.
Yeah, that's a very objective answer.
Yeah.
How are the other teachers?
They're good. I mean, we're all just tired. The middle schools are really bad right now, so we're, especially as freshman teachers, we're inheriting just like years of negligence and deficiency between like COVID and between like this push them through mentality and the proliferation of just tech everywhere, and like they are so just glued to their computers, where like I can't have them unmonitored on their computer for more than a second because they will immediately start playing games on them. They will message each other on like Teams. Like I literally had to lock someone's screen because I was doing an observation in another teacher's room, so I turned on my monitoring like software, and they were messaging about like the boy that they liked to their friends. And, like, dude, I didn't see that, so I locked their screen, and they were very embarrassed when I came back later.
That's fucking funny, dude.
And it's like, bro, come on, that's your school issued laptop. Like, come on, you know I can view what you do.
Dude, we had something like that when I was in high school where like they could like monitor it and the teachers would just like project your screen onto the on the whiteboard, whatever.
I haven't messed with my students too much. I had one student who always keeps playing games, so I locked down his screen and typed a custom message, and I was like, I said his name, and I was like, student, no games. And he was like, oh, come on, Mr. Underwood, why are you doing that to me? And I was like, what do you think? I turned my back, and this dude whips out his computer, and he's trying to play like Retro Bowl or, you know, I don't even know. They have all their games that they play, but
Cool math
The nice thing
games.
about working at this private school is that it's a very strict no phone policy, and they can't use headphones unless they're wired and plugged into their laptop. So I don't have to deal with the AirPods, because that's what I had to deal with in the public schools, was phones and AirPods. So that's nice. I joked that I told the students, I was like, you know what, I will take a pay cut to work at a private school if it means I don't have to see a phone in my classroom ever again.
Really?
Yeah, because that shit is like obnoxious. They're glued to them. I'd very regularly poll the kids in the public schools, and they have an average screen time of about like 8 or 9 hours a day on their phone.
Yeah.
Which I don't know what you guys are
Relatable.
sitting at, but
Well, I'm on a screen for work all day, and I go home onto another screen. So
I mean, like, at least your phone screen time.
Yeah, I don't know. It's probably pretty bad though. It's honestly probably pretty bad.
I average about an hour to 2 a day.
That's pretty cracked.
That's good.
Yeah.
I feel like I'm probably more than that for sure.
I just don't have any social media or like anything. I don't know. I'll scroll
Yeah,
through Twitter
Twitter,
occasionally,
man.
but
And Twitter getting fucking pissed at my phone.
I don't know. I'm just like, I don't have my phone on me when I teach, so there's 9 hours of my day that I'm not on my phone, and I'm not on. I mean, I'm on my laptop, like planning and grading and stuff, but not while I'm like teaching, like I'm interacting with my kids. So.
Right.
But I do come home and just play video games, so.
I'll probably be bored as hell on the teacher. I'll just be on my phone while the kids are doing shit. Like, yeah, do your packet.
No. You gotta get in there.
On my phone.
I've seen a couple of teachers when I walk past their rooms, they're just sitting at their desk on their phone while the kids are working, and I'm like, I have no respect for you.
That is bad, though. Realistically, I'd be pissed if that's what my like kids teacher was doing.
I mean, it's why I like to gas myself up a little bit, because multiple people have told me, and the freshmen have told me, that I'm consistently rated their favorite teacher. So
Good. That means something, man.
yeah. Try to do fun shit. I did we played Family Feud the other day. I pulled 153 freshmen to like different questions, and I made this giant spreadsheet and like organized their data, and I made a custom Family Feud game in Microsoft fucking PowerPoint. And I had like a little buzzer system, and yeah, we just played Family Feud one day.
That's fucking awesome, man. Those
Yeah.
are teachers that make an impact, you know?
Yeah. I like to think I'm doing something out here, man, but other days I'm like, wow, you have no skills. You have no, like, I don't know if I'm making any headway.
Well, you know, kids can be a bit stupid, but they'll appreciate it when they're older.
Some of the things my freshmen say, man, I feel like every now and then I'm talking and I just feel like I've lost brain cells like daily because of the shit that they say.
bad?
Like, yeah, it's like what? When I gave handwritten comments on their last writing assignment, and like I would sit there for like a minute just reading what they wrote out loud over and over and over again, and it just made no sense. It'd be like, the American Revolution was caused that it gave rights, and I'm like, what?
Oh God, man, these
What?
kids are not gonna make it.
No.
Is it
As the
over?
kids say, they're cooked. I've ruined that word for
Kids are
them.
cooked.
I was joking. I was like, all right, guys, we're gonna play a game today, and as you know, I've been cooking on it. And they were like, nah, dude, shut up. No, Mr. Hunter, don't say that. Don't say that. And I was like, what do you mean? Didn't I use that right? Cooking, you know? And they were like, no. I was like, oh, I cooked, right? You know, now I haven't heard a single
That's
student say it in my
hilarious.
room.
You're just like trolling them.
Yeah. I don't let them know that I'm like very up to date with internet culture, but I just like to butcher their silly little
That's
stuff.
fucking hilarious, man.
Man, Q times, man.
Bro, this shoe is pretty grim. I can't lie.
What's one wide match?
No one else is queuing right now.
We're not even that wide.
No,
It's
there shouldn't
not.
be. What's
That's the thing. We're not even that wide.
What's your support?
Only Masters
Diamond,
2.
or Masters 2. Oh, you're Diamond 1 on the others. Okay.
I am, but I don't. I just suck ass.
I mean,
it's over.
I don't really give a shit. I was playing a game of comp last game. Like my team's all malding. I've got a deep house set playing on YouTube. Drinking a Miller Lite. I could care less what's going on in this game. I'm
So
just happy to
tired.
be here. It was a really bad Blizzard World match though. Venture goes like 0-3 trying to flank, has like 1k damage after like a round and a half. It's the type of game where one of my teammate typed GG after the first team fight.
You get in lobbies like that, it's just it was already over. You know, it was already decided.
We were
just
actually
based on-
doing really well, but then the Venture who fed, he was on Echo, and like we were doing like I was going crazy because you know I don't give a shit. I'm just gonna keep playing. And we like took first. We were just about to take second, and then he decides to like emote and just like throw in spawn while we're like contesting point in overtime. And he didn't realize that like we were gonna keep going. I get a nano off on our tank. Like we get 2 picks. I go down, but like our Junker Queen's still alive. There's like 2 on point. And he wasted the whole time just fucking emoting and spawn. And it's like, dude, if you got there, we could have easily. We were like a meter away from capping second. Actually winnable game. And I don't know. Everyone flamed him. They were like, dude, you're a fucking idiot. But yeah, sometimes you lose in matchmaking, right?
Yeah, no kidding.
Can't win them all.
You know, it's like, all right, I'll play one more before bed, but we gotta get a match. Been waiting too long. Stay up a little bit.
Why
9
is it
o'clock's
this
my
bad?
bedtime, so.
I can select DPS. I'm just run with that. I'll just run May or some shit. But
It's up to you. Don't matter.
Up to you.
I can be up
Alright.
for a bit.
which fuck it, bro. This is way too long. It says I'll need to be 5 minutes, but that was definitely longer than 5 minutes for a while.
We'll get a game for sure.
Yeah.
DPS. We'll get a game right away.
Let's see.
Maybe I'll have one more. Oh, I thought I was like,
No.
oh shit. I'll do it.
Who's good on DPS right now? I feel like I see like a lot of people.
There it is.
Oh.
I mean, what are you good at? You know what I mean?
It's like May Reaper. Or what's going on? But this is not a May Reaper kind of map.
This is like a sniper's type of map.
Yeah.
Okay, we have a Widow.
Yeah.
What's your pool? What are your best
Oh.
DPS?
I'm just but probably like, dude, I don't even know.
Well. Look at this. We're in.
I'm trying to figure, I honestly think just playing what you're good at matters more than trying to play what works on the map or what's
Yeah.
meta, you know?
May Widow, look at this.
To a certain extent.
Dare I say we are cooking?
I think we're gonna get cooked.
I say, dare I say? I always say that shit.
I'd probably be cracking up if I was in your class, Joe.
I was like, they were doing their pre-ACT today. I had to proctor it, and I was like, dare I say this would be a light work, no reaction? And they were like, no.
It's funny because you're like purposely making it
Saying it
cringe.
weird.
Like, you know how to use it correctly, but
Yeah.
you're just trying to like fuck with them.
Alright, let's see. Echo Widow, I think. Yeah.
Widow one.
Widow one.
Echo low ground on the right.
I'm just gonna fucking
No.
Sigma flank. You know what I mean?
I couldn't save our Widow. Widow far back. Ow, I took a headshot.
No nade.
Echo on the left, flanking. Sig behind you, I'm shielded off from you.
Oh shit.
Ah, damn, I was second to it.
Forward to 9. We should be pushing third down. Now it's even.
I'm gonna die here. I'm missing all my shots on you.
That's alright. I have an escape. And I shouldn't have jumped. I shouldn't have jumped. I should have just walked. So they have a. Yeah, I could probably run Sombra here.
In my world, there are no secrets.
Oh, our Widow's getting diffed.
Yeah.
Enemy spotted.
Oh, huge.
Nice. Sigga's weak.
On the right.
Oh crap.
No.
I mean,
I'm gonna die to
teabags.
Echo. I'm gonna die to Echo. Or not. Oh god, I'm alive. Thank you. No, dude. I need this Widow to win one duel. Please.
Nice.
Alright, good. I'm coming from spawn.
That is so big. Nice job.
That's huge. I might not be Ana. That Widow's just looking at me.
I have no shot.
I haven't gotten any damage, so I just had to play so back. No.
Oh.
No.
No way. What?
I'm more than happy to get off.
Nah.
You do beat
Their Sig just walked on quiet. That's
What? My kills got cancelled. How the fuck did we lose that?
their Sig just walked on us. I don't know.
That's pretty crazy.
No.
I'm just gonna nano you, Ryan.
Okay, I'll
Just let
call
me
it.
know.
There's an Ana right here. Yeah, I don't know if you wanna.
Oh, you can do it right now.
Okay.
Adaptive circuits engaged. Winston.
I'm shielded off from you.
No.
Fine.
No! Sig, dude.
Holy crap! I just got one tapped.
60 seconds.
I mean, I don't know.
I'll have EMP in next fight.
Sig just walked on me. I'm gonna go.
Todo listo por aquí.
Rally to the payload.
30 seconds.
Aguas. Enemy here. Vamos.
No.
I can go
Stop
cast.
jumping, Juno. Holy shit.
Okay, Cat's here. I must have EMP.
I'm on cast right now. Now they have cast. I gotta go.
Two purple.
Yeah, like no time.
Oh. That's gonna hit me. I'm dead. Damn, bro.
Apagando las luces.
Score 0-0.
Alright, we full hold.
Bro.
Full hold team right here.
Prepare your defenses. Select your
I don't know what support to go here. Let's see what our other guy picks. Sig just kept kind of walking at me, and I didn't appreciate that. We just get some more.
Every soldier needs a cause.
Hello. Seeing you here reminds me of home. Though
What about that?
the smell is quite different.
Make your preparations. Careful research is effective research.
Hello.
Oh, a night mission brings back memories.
5, 4, 3, 2, 1. Attackers incoming.
What the fuck?
Doomfist? Interesting play.
Reloading.
Do miss punch.
You guys. I got you.
Okay.
Alright, they're not Widow.
Fuck.
Big.
Yes.
Could just do that. Just one.
Yes.
Run low, run low, run low. Nice. Echo low as fuck.
Yeah.
They're tracer now.
Watch poles.
Yeah.
What she has.
That's better.
I'm gonna save lamp for it.
I'm riding some bullshit.
No recall. Nice. Shit.
Ryan behind, he's low.
Yeah, Ryan's weak behind. You're kind
I'm
of.
gonna get attacked. I got an eye on you, Ryan, kind of.
Yeah.
This
one. Nice.
He's inside here on the left.
Okay.
I don't have lamp for another few seconds.
Adaptive
Step fire.
circuits engaged.
Soldier's weak.
Soldier 76.
Cappy's slow. Cappy's flanking. You can all blind her.
Yeah.
You can die. Oh, no, you can't die.
Watch Shatterson.
I don't have lamp. Tracer behind.
Oh.
Echo low, echo low. Got her.
Nice. Just Ryan over there. Yes, Shatter. Care Shatter.
I gotta kill him.
Nice, nice.
Okay, so they have a minute. We have only Juno out next fight. They have Widow now. Watch Widow.
60 seconds remaining.
They have Shatter. Widow. Probably Nano coming up.
Just, yeah, Shatter Nano.
Oh yeah, I should not do that. Yeah, Widow. No recall.
Yeah, they're just playing for Shadow.
Widow one.
Pretty much.
No way.
Oh, no.
I reacted that so late. I didn't realize I was doing that. Oh. Care Shatter.
Pretty bad.
No, I thought he was gonna take you into the wall there.
I think we get a retouch if we go fast. You live?
Yeah, try to live. Try to live.
Okay, the Nano Tracer.
They're gonna
That's
come
bad.
in with Nano Ryan.
They Nano Tracer already?
Tracer. No.
Why'd this person stay
Oh
there?
my god, you guys were all 3 2.
Do I need to
I
touch?
can't
Yeah,
touch.
yeah, you gotta touch it.
Fuck, I should have waited. Oh, dying with ult, man. Oh,
Dude.
that was so winnable.
Yeah.
GG.
Shit, Juno was like, didn't hear the. I don't think our Juno had audio or something.
Play of the game.
Oh, but Skurs played the game, so we win.
No.
Sure.
Filthy, nasty. Huge rock.
Huge rock.
Okay, I was about to say, you get one more kill. I was like, I mean, quite the play. Damn. Oh, I got demoted.
Same. Wanna do one more? I found my flow on Soldier.
I'm down.
Okay, okay.
Yeah.
I got one more.
Okay.
Then I gotta get in bed.
Yeah.
Gonna be up at 6 a.m.
Oh man, that sucks too. I also gotta be up at like 6.
Ooh, good. Quick kill. Diamond 2 to Masters 4.
Joe Biden Pog. Good.
Okay, it's the same.
Same people.
Is it?
Yeah, Joe Biden, Pog, Falcon.
They don't have PogChamp anymore though.
They don't have PogChamp. So yeah, just those two.
Every soldier needs a cause.
I heard Talon failed another mission. Going soft?
Do not speak to me unless you wish to.
Wait, what's the
I
ping?
think this has gotta be like the
still be the
ugliest
better
soldier
shot.
skin.
Oh
No,
my god.
it's
What is that?
fucking
Like a
goated.
watermelon head.
What the fuck
That
is
is
this?
so bad.
What is this?
It's nice. It's called
This is what I have to say about that.
Je sens que je vais bien m'amuser.
it's called Moomin Rider. It's from the.
Watermelon on your
Go
head.
get the beach ball.
It's-
Ready? Go get it.
Alright.
It's my favorite thing to do is hit that and then see like client side where your beach ball is versus where mine is.
Let's get this
Jung.
Yeah, this might be some fucking bullshit.
No gold chop.
There's
Got
no
it.
guard here.
Ow.
I'm just gonna hide him.
Ooh.
Okay.
Yeah, I can't get to you.
Wow, they have
Reloading.
Venture and Junk. Ooh.
Now's the time
Echo.
to play May if that's your hero. Good round if I can tank though.
Ready to learn.
Yeah, we can stabilize. Venture coming in.
Venture's gonna feed.
Choose one. Nice.
Let's go time.
Juno up there. Brig one, brig one, brig one. Damn.
So much.
No.
Nice.
I got you.
Thanks.
Reloading. They're gonna touch.
Hope not.
No rock muncher.
Props cause you like beach.
Sure.
Or what is not like? I mean, there? What is Venture's
There.
program?
I keep saying she on accident, but it is there.
I mean, Venture looks more feminine than masculine, but you know, there.
Gonna save Zed. Alright, look at unit. That's coming from my ass. Huge.
Okay.
You can
Now, what's my diva doing, bro?
Come
What
on,
is
then.
my diva doing?
No.
Oh my man, I got
fuck.
whip shotted.
Are moving. Wait, we're playing through
Oh my
fucking-
god.
They have a
Widow got us killed.
crap. They have rally.
Fucking hard. Do you see what our Zen is doing?
Oh,
No one can hide from my sight.
look at the Juno purple. There we go. Diva half. Diva one, Diva one,
Diva
Diva
after
one.
one. We can just leave her.
I mean, she's gonna fucking kill
I
my
gotta
ass.
get this player, so-
Holy shit.
Did their brig die?
No, she's up top. Tracer over here.
Don't die for it.
I won't.
Got big kill.
Bait it.
There's Sombra.
Oh, I fucking. Yeah, I'm hit.
Oh crap.
What the fuck? Are you kidding me?
Oh my god.
What the fuck?
Big purple, big purple.
Nice.
Good.
I died to a camera. LOL.
On Hanzo and Ryan.
Reinhardt now. This match is so confusing to me. It's just like all over the place.
I'm on cart bitch.
What the fuck?
Am I not?
I'm ramping here real
Oh,
god damn, I
fuck.
didn't get to.
Ryan's
Hans-
super one,
someone's
but
one.
I don't like that
Some-
for it.
Yeah, we have Shatter. I mean, chance. They have EMP soon.
What is this actual game? But it's like sometimes I just don't know what's going on. Like, why is Ryan charging on fucking Echo?
What is this?
Excellent question for another time.
Zenyatta's freaking goat apparently too.
Yeah, he's popping.
I'll have to let him.
Watch EMP.
Like, what is that Sombra too?
Oh god, dude. No, my first death.
Enemy in sight.
Yeah, surely with this, yeah. Alright, we're good. Damn, man. First death. Feels bad. Yeah, our Zen was fucking going crazy.
Our Zen? I don't know what the fuck you... He should have been punished, but he just never was.
Yeah.
He's just in places where he should not have been, and...
Prepare your defenses.
I'm Ginger.
Select your hero.
What have people been typing all day? Let's see. Tactile camera. Everybody has to name himself Feet Smeller. It's level on.
You guys hear about the case in the dorms a couple of years ago where there was a guy who like broke into this girl's room and like she like woke up to him like sucking on her toes?
Oh yeah.
I feel like I heard about that. It's just like a legend that everyone knows.
I don't know, bro. I don't know.
Is that true, or is that sounds like some bullshit something stuff?
It sounds like some bullshit, but I don't know, bro.
It's also believable, but I don't know, how do you break this one's door?
Just leave the door unlocked. I slept with my door unlocked.
Really?
Yeah. But
why?
It's because I come from like a small town where like you look, you don't need to. But
that's no reason to be careless.
like my apartment door right now is not locked. But
I couldn't do that, man.
Never.
Attackers incoming.
I definitely couldn't do that shit at my old apartment here in Columbus. Maybe my current one, but...
They want to play Doomfist, but it's just not the pick.
What the frick?
Oh.
Oh my god, man, they open.
Everything. I got you. Oh, I missed. No. Sorry, I had Doomus in my ass. Make sure our support's I got you in a sec.
Nice. Holy crap.
Let me go up. It's my home now.
Got eyes on an enemy.
They have no, they don't have it.
Oh, Doom has punch. Watch out, Widow. No, boys. They're just gonna have to die.
My monkey, but I don't know if I should have.
That was weak.
I never
I mean,
hold up
Doom's...
here, but this is my spot now.
I mean, it seems pretty safe there.
Doom
purple,
one.
Doom purple, Doom purple.
I need to get out. Oh shit, Doom jumped here? Oh fuck.
I'm dead. Fuck. You guys are fine though.
Doom is super
Get
long.
back. Alright, our Zen's alive. There's hope.
Adventure 1. Nice. I think Doom's kind of weak too.
With our Zen.
I think it's winnable. I think can someone touch it?
No
way. Shit.
Oh no, it's not winnable anymore. No. No way.
Fuck. I definitely got our Zen killed. Oh no, that wasn't my name that killed him.
We should go fight high ground.
Doom.
There's one.
Try to kill him, but
I'm dead as fuck here. Our Widow's getting boomed.
we need to like, I don't know.
Yeah, we just gotta reset. We
just
fine.
got out there.
Okay, they're on
Okay.
Zen Lucio now.
I'll stop.
Like, yeah, their top sucks.
Smiley face.
Doom's looking at me.
No way. Oh, it's because I had Discord on.
Lucio on me. Oh. No, bro. He's one.
I have no words. I was trying to
I
kill
feel
the
like
monkey.
you should not do it. Do something else. I don't know.
Come on.
Keep going. Huge primal. I'm almost back. I've got nano. Do we need? Are we good?
Nah, we're good. We're good.
Okay.
I think.
Oh my god.
Can you have me? Can you have me?
Yep.
I think that's the right call. Yeah.
Venture on point. Oh, bro, Venture pisses me off so much.
Yeah.
What is? I feel like their cast time, the dig, should be low.
We gotta live. We gotta just live here.
Like that shit is instant.
Yeah, it is.
I don't think they're like a busted character. Okay, dude, our Widow's gotta switch.
Yeah, Widow's gotta switch for real.
Fuck.
There's always down something, you know.
All purple, all purple, all purple.
I can't.
I'm gonna die to Doom.
So one.
Lucio one.
Tracer asleep here.
3, 2, 1.
Oh fuck.
That's
alright. I didn't think anyone else here. Lucio one, Lucio one, Lucio one.
Yeah.
Okay, we're good.
Yeah, that's...
Doom on point alone.
Nice.
Alright, I'm gonna try and get up on high ground. Damn, I didn't 5-head that enough.
I think I'm Zen. I'm just waiting for a window. Don't go too soon.
This is weak too, but
Where is Zen?
he's underneath, I think.
We gotta look at point, they're on point.
Well, the both their supports are
Oh, they're C9ing.
Oh, C9.
We should be okay there.
Oh, fuck. There's no way here.
I'm gonna die on point.
I mean. I can just live.
Okay. Body's almost back. I'm almost there. Stay up. Peek window. Nade to you. No.
That's low though.
Oh my gosh, for the AoE on that.
Oh.
What's going on, man?
I'm gonna get this nano off. I don't know. I don't know what to do. I feel like I should be fine if we can ever just get like a normal fight.
Let's use it.
Window. I guess. Oh, my name is
so low.
No one can hide.
Do you know my ultimate is charging?
Oh, Doom's gonna fucking kill me. Bro, why does he? Fuck, the slow man.
No, wait, how did I not get manga? Carry one.
Carry one. Got a bitch ass.
Doom's coming for you. Okay.
Oh.
Gotcha. Smiley face.
The Iron Forest watches over you.
Carry one. Lucio pushing me.
Holy crap. That. Nice.
Carry is one. That's one.
Yeah.
I got nano.
You can have me, but I'll call. Anyway. When Doom jumps in, now me. Yeah, you can have me.
Nice Ajax.
That was incredible. That
Doom behind. Behind. Yeah, I Can't see. There's an aid.
Thank you. The fact that he tried to beat in front of a Nano Diva.
That's crazy. Yeah.
We're gonna rush here. Maybe the VP as well.
Okay, I think we just kite that.
Yuri won. No cleanse. She's one. She's one.
Sunburn one.
Fuck.
I can't see you.
Be okay, maybe.
Doom purple. Doom one. Doom one.
Oh, that killed me. They take for us.
Yuri, no cleanse. No cleanse. I'm dead. Fuck. Yuri one. Yuri one.
Oh, they see
They
that.
see nine. Holy shit.
Wow.
They see
Holy crap.
nine.
Huge.
I mean, I think we were winning that.
Yeah.
But I no way.
I mean,
they
we
see
we
nine
capped with
like
like 3.5 minutes, anyways. So.
Awesome widow.
But.
I'm Ginger _3. Smithing on widow and complaining about venture.
I mean,
Thank
okay,
you, I
Sunburn.
love you.
Good shot. There you go. Who is this guy? Is this Kefri?
What?
Kefri confirmed?
Yeah.
I had a game with Kefri the other day.
That was
That
uphill.
was an
man.
uphill battle. Look at that.
Wow.
That
Still
was
feel like I got the same amount of percentage for a normal win, but
I just don't even know what to make of that match. It was just all over the place.
Yeah. I would be upset if I was enemy team and that was like expected. Wanna go again?
alright,
Or you gotta go. No.
I gotta go to bed.
Alright.
Oh man.
I'll play some other time that I can actually queue.
Alright.
Try to get my DP or support up to fucking masters. That'd be good.
Yo, yeah, dude, that'd be sick.
Alright, GG's guys.
GG's, good night, man. Peace.
Please, yeah.
I'm gonna go pee real quick. I'm back. Okay.
Welcome back.
Thanks, man. Yeah.
If we win this one, I might go get food.
Okay. What if we lose it?
I don't know. Then we gotta win.
Yeah. Are you friends with a lot of your coworkers?
Man, they used to be.
Oh, because they got laid off.
When I started there, yeah, we were just hiring like I've been at the company 3 years. Actually, this month is my anniversary.
Oh wow.
When I started, we were hiring a bunch of people, and it was all like young people like me, like who had just graduated college or something. Everyone was like 23, 24, 25, whatever.
Mm-hmm.
And it was great, man. It was so fucking fun. Like we would just fuck around all the time. But yeah, I'm still friends with the people that are left, but it's just like, this is not the same.
Not the
Like,
same.
there's no one at work now that I would hang out with outside of work.
Prepare
Damn.
for battle.
Okay.
Select your
This title fight guy is the one trick Genji, and he smokes my ass. So I hope he's still the same goat.
I gotta play Orisa here, low key.
Perhaps.
I don't know if I should force it. I feel like my Orisa could be good if I sharpen up on it a bit.
I'm sure if you just think about your cooldowns, it should be cool. Just chill.
Orisa is just such a dumb hero for some reason.
Yeah.
Alright, I don't want to throw this game though.
SKRZ.
I'm just gonna watch it.
One small step at a time.
I'm gonna watch some infected videos.
5, 4,
How to play Orisa.
Oh, you've been watching Infected?
He's pretty good at everything.
Yeah, it is. It's interesting. Makes me wonder like what goes on in his brain to make him like good at tank.
Yeah. Oh shit.
Fuck.
I don't know if I should have done that. We almost got the tank straight there. I wanted to push Queen in, but she might just
Yeah.
killed us by doing that. Okay, I feel good about matchup. Oh my god.
Oh crap.
Finish the one though.
One of it. More half.
Put that down.
Okay. Let's see. Watch Queen out here. We don't have beat.
Okay.
for the reckoning. Adaptive circuits engaged.
Queen one.
Lost. Next, flashpoint, the ducks. Pick it up.
We must accelerate.
Step right up.
Queen's behind us.
You know. Nah, never mind.
Queen can die.
Oh, kind of weak. Nice. Marina Finn.
I gotta reload.
Yeah, nice. They have Echo now. They're gonna have probably Juno Waltz. They have Zar. They have Cole. Echo's main.
Oh, jeez. This thing. Oh my god.
Yeah. So I think our Lucio was like AFK. No way, bro.
Oh no.
My B. I get it.
That is bad.
That's my bad. Fuck. I meant to press tab. I meant to press Q. Shit.
Yeah, man.
Step rider.
Grab.
Lost.
Chang.
Flashpoint refined.
Are you okay?
Venture here.
What did I do?
Thank you for assisting.
Hello there.
You can watch Venture out here. And Duke. Fuck.
Adaptive circuits engaged. Venture.
I don't know why Jungle Queen's talking. Yeah, they were the one playing Lucio and Moira.
WTF, You're on Moira and beat nothing.
Play of the
What's that live? That guy.
Maybe one more.
Okay.
One more.
Apparently, there's a mobile version of Overwatch in development.
There's a what?
A mobile version of Overwatch, so you can play Overwatch on your phone.
Interesting.
Yeah, I think that'd be really hard.
I mean, it's on the Switch, right?
Yeah, I guess that's true. I guess if everyone has like bot movement like on your phone, then it's probably not so bad.
Yeah. And just console Overwatch in general. That's good.
Yeah.
We'll continue this while not logical operator q dot is empty method. While our queue is not empty, pull each element and display it. So within a print line statement, let's use q dot pull to display and remove each element, beginning with the first one. And then working our way to the end.
I think I got HTML and CSS down. Now I gotta learn JavaScript.
Have you been doing like some sort of guide?
Yeah, I've just been watching a YouTube video on it. It seems pretty easy. Well,
yeah,
like
yeah,
HTML is easy. But the CSS seems pretty interesting. I don't think it doesn't seem that challenging. Well,
it's I'm gonna say it's not. It's just, you know, there's just a lot of learning. You just gotta start doing it.
Yeah. I think everything doesn't seem too technical. It seems like you can like Google or like.
I mean, CSS just gets there's like a steep learning curve once you start doing stuff.
Oh well, I guess how much of I guess I don't know actually, because there's some clean looking UIs out there, and I guess I don't know how you would achieve that using only CSS.
What's that?
There's some like really like I don't know how you would make like YouTube's UI in like CSS.
Yeah, that's what I mean. You gotta like.
That's pretty steep actually. Or is that done in React or some shit?
Yeah, I don't know. I don't know what app it is, but I mean, at the end of the day, it's all going to be HTML, CSS, and JavaScript. There's just frameworks that kind of make it easier to do those things.
Prepare your defenses. Select your hero.
So like when you're like implementing stuff in like CSS for your, do you work with CSS much at your job, or is it primarily like JavaScript with like Vue?
I haven't been doing a lot of front end stuff.
Right.
If I was, then you know, every design obviously needs CSS. Yeah, I'd say it's pretty typical that. I mean, yeah, whenever you're doing front end, you're gonna need to do all three.
Oh, I see.
But
back end, you probably don't.
No. We have a designer, that makes the designs, and then as an engineer, you just have to build it. So once you kind of learn how, the right CSS classes and stuff, you kind of figure out how to do it all.
Oh, fuck. Yeah, I'm done.
We must accelerate. Enemy over here.
They're like pushing.
I need help.
I mean, I don't know. This person
The payload has reached.
wanna play a life weaver. It's a mercy player.
Unable to invite players to your group while they are in competitive play.
Increase our pace.
I can go brig if needed, but
Nah, I think they do. I really want him. Don't know how we're just getting pushed on.
Let's take off.
The payload has reached the checkpoint.
They're removing the payload.
someone's over here in this room. There's a brig here.
You probably die for them. Bro, like, what the fuck is going on in this game?
No way, bro.
What?
I'm trying to brig out.
Wow, how are we doing nothing in this game? What's going on?
Cover each other. We need to stop that payload. Take this. Over there. I'll come and be known.
One primal went down on him. We're gonna play it again.
Sending care your way. Stop that payload.
Of course.
Looking out. Focal point. That's how it's done. Here, take this.
How the chance to get up there? Oh. What? I did not know that was a spot. Holy shit.
I'm gonna go on this fucking pedal.
No.
No sweat. Just try
1 to 3.
Hmm?
Score.
My
3
kid
to 5.
0 to 3.
3 to 5.
Switching sides.
Match. 3 to 5. 1 to 2. Avoid your tank.
Oh, this is the guy from the last game.
There we
Oh,
go.
is it the guy from last game?
Forward, since it's a team game. 0 brain cell. Brew, are you the Moira from last game? I'm your father.
I'm your father.
LMAO.
I can't tell if
Can you
that's the
come
same.
home? I miss you.
It is the same person.
Hello.
Breaking
Is what it is.
SKRZ. Crew. Team. This exactly why I left you. Only LW. 1 to 3.
So many memories.
Are you guys having a divorce mid-comp game?
5, 4, 3, 2, 1.
One small step.
This is a one-sided relationship.
Escort the
Pick up a dust storm. Enemy over here. Thank you for assisting.
What the fuck? I didn't get gripped.
I must not panic. I am fine. Locking satellite vector.
duplicating boogie.
I'm gonna go on this bag with you.
You're super blind.
Done.
Thanks. Why has the payload stopped?
Forget to breathe. I am breathing.
I watch pulse. Wait, no one's pulse. Monkey really won behind.
Apologies. You were in my flight path.
Okay.
I am escorting the payload.
Fuck, I got body block.
Oh, that's person behind it.
Let's increase our pace. Get in there, Bob. Locking satellite sector.
Big one.
That sucks.
Duplication.
Come on, everyone.
Payload is moving right along.
Yeah, that's good pull. Fuck, bro.
60 seconds.
It's Hanu.
No, wait. I am still here.
Okay.
30 seconds remaining.
Watch here.
Monkey up top.
Light speed.
Where'd you go? Nice.
Well done, Judah. Let me help. Let's lock in satellite sector.
Fuck. Last one.
I've got primal. Can you say point?
Yeah.
I'm trying to get bridge.
Back here.
I'm not getting it now. He's gonna die.
Original one. Crap.
Complete.
Yeah, we have to work hard for this one.
I know.
Score 3-3.
One small step at a time. Pre-mission checklist complete. Now it's time for the good bit.
Saddle up. We got work to do.
Stay near, will you? I hate when people run off without me.
We're gonna do that.
5, 4, 3, 2, 1. Attack commencing. Escort the payload.
Smoke 'em at me.
I'm gonna get sharp by guys earlier.
Oh, I just can't cross.
Breaking me down just builds me
We don't
up.
have much longer. Time to clutch this.
Looking better already. I'm under fire. Shield buckling.
Oh my gosh.
Team
Okay,
round
I'm ready to go again.
complete. Score 3-3. Switching sides.
Hello. Hey.
I don't know. I
How's
just
it
feel
going?
like
Fire
of us.
just builds me up.
Hit with the wall.
You look like a talented bunch. This should be quick.
One's on your back.
5, 4, 3, 2,
How's it going?
1.
Thanks.
Attackers incoming.
How's it hanging?
Everyone push
Stop
the
the
payload.
payload.
Nice.
Shield buckling. Enemy over here.
We're gonna have to contest this before it's too late, though. But time for that. I can't do it.
Okay, and then
GGS. GGS. GGS.
Alright, I gotta go get food.
alright, man. I got it. Alright.
Later.
Later, man. I might do one more. I'm calling it.
So this will display the elements within my queue. So these are in first come, first serve order. Whatever element we were offered. First, we are serving.
Oh, I should have avoided this.
Hello.
One small step at a time.
Stick with me and you'll climb straight to the top.
Five, 4, 3, 2, 1. Attackers incoming. Defend objective A.
Watch yourself!
Tracer coming up.
My ultimate is ready.
I am ready to raise
My quiver, you stupid bitch!
Objective lost. Stop the payload.
Yo, you are. Yo. Fucking god.
What happened?
This kid is trying to give me such a big touch point. He just keeps going up on his fucking leaf in the air so he can't heal me. So I go for the recon.
I'm not good. They're not in voice. I think it's just a mercy player. But I'm not sure.
The name's Cassie.
Yo, hey, I'm about to beat the fuck out of this life.
What's up? Enjoying the meal? There's one.
Someone's pushing. C9, C9, C9. Really one. C9. Okay, what do they have next fight? Another Queen ult probably. Maybe another Pulse. Big stagger. Watch Queen ult. And then Pulse.
Health.
Time for the reckoning! Destroy him, Bob!
I almost had Juno ult. We could have won that.
Maximum velocity!
Nice high.
Watch Mail.
Time for the reckoning!
Most calm game of Overwatch.
We must accelerate!
Make this a habit. Step right up.
Complete. Enemy target located. Score 0-2. Switching sides. Prepare to attack. Select your hero.
Match. From the screen to the ring to the pen to the king. Goat song. So cold.
Coming for you. You leave a winner.
One small
or
step
in a
at a time.
You know what's also cold?
Cole Cassidy. Cole Cassidy. Cole
Winter.
Cassidy.
You called?
I just like saying your name.
A bottle of prime
That's all.
energy.
I wish violence never solved anything. It would make peace so much easier.
5, 4, 3, 2, 1. Attack. Capture objective A.
Come here, will you?
I need a medic.
Ladder. Excuse and that flashy.
Spotted an enemy.
Okay, I have a general. I don't think they'll have any else. I just want that.
Yo, are you guys on 100 ping?
Nah, I'm on 60 though. It's not my server.
Duplicating
Safety in numbers.
Okay, I don't think they have any else. We should have been with. Maybe they have nano, but we should have been with Cage. Sig behind. Why are they picking that?
SKRZ. Team. We all go high ground.
Orbital ray is ready to fire. Orbital ray is ready.
Okay, what do they have next fight? Molten Core? Probably Nano.
My ultimate is ready.
Sig really won. Sig won.
The payload has reached the checkpoint.
I am done for.
Okay, they'll have Bob next fight, I think.
Wait.
Bob Nano.
Nice high. Over there.
Feel free to join me.
Let's increase our pace.
Hello.
Enemy discovered.
Fuck, Ash is weak.
Do something.
I'm sure we can move that payload.
60 seconds.
I will help you. Let's increase our pace.
Yo, coming at you.
Orbital ray is ready.
Light wave back here.
My ultimate is charging. Fix that.
10 seconds remaining.
Hyper ring out. Welcome to orbit. Enemy over here.
GG. Match. GG. GG.
Play of the game.
Time for the reckoning!
element first. If an element was added last, well then it's served last. So that's a standard queue. Now with a priority queue, we're going to arrange them in some sort of order before we actually pull these elements. So let's change our linked list to a priority queue. And run this again, and let's take a look at the differences. Okay, these are all in order now. So if we're working with numbers like doubles, these are arranged in ascending order, beginning with the smallest element. Let's pretend that these are grade point averages, GPAs. Why might we want to put these in order? Let's say whatever student performed the worst gets 2 hours of free tutoring, whichever student performed second worst gets 1 hour of free tutoring, and third gets half an hour of free tutoring. Now, if you need these in descending order, well, there's one change that we're going to make. Within the constructor, we can pass in a comparator, but that's a little advanced for us and we haven't discussed that yet. So there is a default comparator that we can use found within collections. Collections dot reverse order method. So these elements will be in reverse order then. In this example, let's say that whichever student has the best GPA will receive, I don't know, a gold medal, like the Olympics. And the second best student will receive a silver medal, then a bronze medal. And then every student after that, I guess, will receive nothing. But that's okay though, they got some free tutoring in the last example. Okay, now let's change the data type. Let's say that these are now strings. And let's put these in standard order. So let's change these to strings. Maybe this student has a B. This one has a C. A. F. And what are we missing? D. If we have a priority queue of strings, well then these elements will be in alphabetical order. So if we need these in reverse alphabetical order, again we can pass in a comparator, and then one that we can use is from collections. Collections dot reverse order. And these elements within our priority queue are now within reverse alphabetical order. So yeah, that's a priority queue. Think of it like a queue. However, we first sort these elements based on a certain priority. We will pull and serve the elements with the highest priorities first, and work our way to elements with lower priority. So yeah, that's a priority queue. If you would like a copy of this code, I'll post this to the comment section down below. And well, yeah, those are priority queues in computer science.
What's like the running time on that though? Okay, I'm gonna go to bed now. Oh. Wait, I can make this a 10-hour stream and 24 more minutes of studying. Should I do that? Fuck it. I'm gonna go pure. let's look at something. Okay. Let me see what I'm gonna learn tomorrow. And then I'll just like do a review on that. Let's look here. So schedule. Let's watch a video on Dijkstra's algorithm.
Today, I'm going to teach you how to run Dijkstra's algorithm on a weighted directed graph. Dijkstra's algorithm tells you the shortest distance from one node to every other node in the graph. This differs from prims and crusticles, which result in minimum spanning trees. Let's use the following graph for our example. We'll keep a list of unvisited nodes at the bottom. Our first step is to pick the starting node. Let's choose A. We'll use the table on the right to keep track of distances. Remember, the distances we are measuring are from our starting node, A. We put 0 for A and infinity for the others, as we haven't visited them yet.
Oh, wait. I should be doing. I was looking at this.
The next step is to examine the edges leaving A. We can reach B and C from A, so let's update the chart with the corresponding costs. Next, we look at the chart and pick the smallest edge of which the vertex hasn't been chosen. In this case, the starting node. Let's choose A. We'll use the table on the right to keep track of distances. Remember, the distances we are measuring are from our starting node, A. We put 0 for A and infinity for the others, as we haven't visited them yet. The next step is to examine the edges leaving A. We can reach B and C from A, so let's update the chart with the corresponding costs. Next, we look at the chart and pick the smallest edge of which the vertex hasn't been chosen. In this case, C. Let's cross off C in the unvisited node list, marking it as closed. After choosing C, we examine the edges leaving C and update the chart accordingly. B is now reachable from A with the cost of 3 by traveling through C. Also, D and E become reachable for the...
Wait, let's... These guys explained it well last time, I think.
So what have we got here then, Mike? Tell me.
Well, we have a strange graph drawn out on my page. A comment on a previous video asked about Dijkstra's shortest path. Now, I happen to have implemented Dijkstra's shortest path for one of the pieces of research I was doing a few years ago, so I thought I'm at least somewhat placed to give an opinion on it. So let's talk about Dijkstra's shortest path. What it is, where it's used, and so on. Pathfinding algorithms are obviously quite important. Right? We use them all the time on Google Maps or on our sat-nav system. Right? There was a recent video on satellite navigation and how it works, but of course that's only half the story. Finding out where you are exactly is the first part of the problem. The second part is, I want to go over here, what's the best route to do this? Okay? Route planning also comes in on things like routing. So if you've got a network and lots of routers, what's the best way to route those packets through which ports to get to your destination quickest? So things like this. Now, Dijkstra's shortest path sees a lot of use in all of these things and extensions of it. So for example, A-star search. So I've drawn out an approximation of a road system on this piece of paper. So we're going to use the analogy of roads for this one because I think it's a good example of Dijkstra's shortest path. And we're trying to start here at S and get down to E. Right? This is broadly speaking a small version of what a sat-nav does when you say, how do I get there? Right? Now, each of these nodes represents a junction. So the vertices on the graph. So A could be a roundabout, B is a T-junction, doesn't really matter. Actually, B is more of a roundabout because it has 4 outputs. Anyway, each of these numbers represents how hard it is to get along that road. So that, in real life, would be whether it was a motorway or a highway, whether it was a country road with a load of potholes, maybe there's a tree down it, and so you can't get through that road. Right? So in the Dijkstra implementation that I am familiar with, and most Dijkstra implementations, smaller is better. Okay, so broadly speaking, this route here is kind of like our motorway, right? 2s, 1s, that's good. This one is a bit of a faff, you know, 4s, maybe middly A roads, right? And this 7 here, that's you falling in a Ford and you know, you've got water in the engine and it's bad. The question is, how do we find a route from here to here? Now, of course, this is a small graph. So actually what we could just do is just search all the way through it by hand or using a very simple sort of brute force search approach and kind of get the best go, right? But if you think of the UK or the US or some other country's massive road network, we can't afford to do that, right? We have to be a bit smarter about how we look through. And we also want to know absolutely that once we found a route, it is in fact the shortest route and we didn't just miss one. What Dijkstra does is basically similar to a sort of brute force flood fill search through this space, but does it in a kind of in the order that makes most sense based on how fast these roads are. So it'll check the quickest roads first. So to do Dijkstra, we need a few things. First of all, we obviously need our graph, right? And when we need some idea of how long the path is to, let's say, B, once we've calculated it, or something like that. So at the very beginning of our search, we have S. We are at S.
S for start, right?
S for start, yes. Which confused me because some of the other letters are just in order and then these two aren't. But anyway, S has a distance of 0, right? It costs me nothing to get to S because I'm already there. Everything else, I'll just put a couple out just to show you, A, B and K, have a distance of infinity because that basically says we haven't looked yet. We don't know how far. So for all we know, it might not be possible to get there, right? And finally, E is just the same, distance of infinity, but with a smiley face to say that we've made it, right? Now, this structure here that I'm going to create is called a priority queue. Each of these will have a distance, but they're ordered also by that distance. So the shortest one's at the top. That's important. And we'll do it as we go through. So let's start our search. We start at S, and we look through the neighbours of S, and we say, right, well, A, it cost me 7 to get to A, right? It's a bit of a pain. So we were at 0 distance, cost us 7, so now we're at 7, right? So A, I scrap my infinity, and I write 7. Right, so A is 7. Okay? A is still the second shortest path currently because all the others are infinity. Yeah? B is 0 plus 2, so that's 2. So let's just put a 2 in there.
This is all even though we haven't actually got to the end yet. You're just looking at the numbers.
We can't get to E without having a look through all of these junctions. So this is what we're doing, and we're working our way in a smart way. Now, B is in this priority queue, but it has a lower number than A, so it takes its place at the top of the line. Okay? So that's good so far. Finally, the only other thing connected to S is C, which has got a weighting of 3. So let's just find C in my list of course, shuffled thingies. There we go. And hopefully how Dijkstra works will start to become clear once you see what I do next. So C is 3. The only other thing that, of course, I forgot is while we're doing our search, we have to keep a track of where we've been. So B, for example, we know has a distance of 2 through the path S. Okay, so S was the previous version, right? That's also true of A and also true of C. Now, we swap C and A, so now we have them in order. All the others are still infinity. Now, S is done, right? So we can take S away and put it in our finished pile over here, right? S we don't need to worry about anymore. The next step is to see where is the current shortest path. Well, it's B, right? B's got the lowest number, so let's start looking at B. So if we look at B, we've already been to S, so we ignore it. We can go to D, so let's put in a D, and D is the distance to B plus whatever this road is, which is 6. 2 plus 4 is 6. And the route through D, which is shortest, is currently going through B. And we'll put that in. Now 6 goes in just above A. Okay, there we go. Now, we can also go to B from A. We haven't finished with A yet, it's just sitting in this queue. And currently the distance to A is 7, right? But actually the distance to B was 2, and the distance to A from B is 3, which is 5. So actually, taking this detour here, which looks longer, is actually shorter because of this tree on the line or something like that, right? So remember, you know, this isn't representative of the actual physical distance from S to C. So we've updated D, and A is now shorter, right? So we take our A, and we say, well now, the route is 5, not 7. It's decreased. And it's no longer the shortest path from S to A, it's from B. So we scribble out S, right? I'm getting too much text on these, but we won't worry about it. So A now overtakes D in our priority queue, right? So that's looking good. Okay, H, B had a length of 2, H has a length of 1, so H has a distance of 3. B is done, right? We've done B, we can count that as done. So C next, right? So we're here. We can't go to S, we can only go to L. That's a nice easy one, so I need to find L. So L goes to C, and it's 3 plus 2 is 5. So L comes in just underneath A like this. So C's done, so we look at H, and we say what's next from H? We can look at F, so F will get 3 plus another 3, so that's 6 via H. And then G is H, which is 3 plus 2, so that's 5. A next, we've already been to S, we've already been to B, so we start to get a little bit faster now, we've seen some stuff already. What we're basically saying is we know what the shortest path to B is because we've already seen it. So we can only look at new things. So we look at D. D is currently 6 via B. A is currently 5. 5 plus 4 is 9, which is bigger than D already is, so we make no change. The shortest path to D does not go through A, so we don't worry about that. Okay, A is done. Next up, L. L can't go to...
Let me see. Yeah, let me just make this visual representation. It's gonna help.
To understand what Dijkstra's algorithm is and how it works, let's start with a scenario. Let's imagine that we have a variety of different towns scattered in different locations. Some of those towns are connected to other towns with roads, such that we could travel along a road to go from one town to another. Not all roads have the same travel time, though. One road might take 3 minutes to travel through, while another might take 4. And our question is this: what's the fastest way to get from town A to town B? This is a specific example of a more general problem in graph theory, where we have vertices, in this case our towns, that are connected by edges, in this case our roads. Together, the vertices and edges form a graph. And in particular, this graph is a weighted graph, because each edge has some value, or weight, to indicate how costly it is to travel along that edge, measured in either distance or time. And with this graph, we'd like to determine the shortest path from one vertex to another. So how does Dijkstra's algorithm allow us to do this? Ultimately, we need to figure out how many minutes it will take to get to town B. In doing so, though, it might be useful to figure out how many minutes it would take to get to the other towns, too. So ideally, we'd want to label each town with a number, representing the shortest time required to get there. But of course, we don't know that information yet. So instead, we'll label each town with the shortest time we've found so far to get to that town. Before we've started the algorithm, we don't have any known way of getting to the towns, so we'll label them all with infinity. The only town that we can label correctly is our source, town A, which we can easily label. We're starting there, so it takes 0 minutes to get to this town. Once we've found the shortest path to a town, let's call that town explored. For all other towns, we'll consider them unexplored. We don't yet know what the shortest path to them is. So what can we do next? Dijkstra's algorithm repeats a 2-step process. First, we update our estimate.
This YouTube channel is just called Spanning Tree and it's 200,000 subscribers. What does this guy do?
In 1997,
oh, he just teaches like big ass like data structures. Expression and propositional logic. This would have been useful a year ago. Math behind Tetris. That's pretty sick. How fast can you? I mean, Dijkstra's algorithm. I mean, he doesn't have that many videos. I remember watching this video. Dynamic programming. I'll watch this video and then I'll watch that one.
And second, we choose the next vertex to explore, what the shortest path to them is. So what can we do next? Dijkstra's algorithm repeats a two-step process. First, we update our estimates, and second, we choose the next vertex to explore. So let's start with the first step, updating our estimates. We know we can get to town A in 0 minutes, and because we can get from town A to town C in 3 minutes, we know we can get to town C in 3 minutes. That's much better than our current estimate of infinity, so we'll update our estimate to be 3. And we can do something similar for town F. We can get there in 2 minutes, so we'll update our estimate. After we've considered all possible roads connected to town A, we're done with this step. And now the next step is choosing which town to explore next. And the rule is quite simple. The town we explore will always be the unexplored town with the smallest estimate. In other words, the next town we explore should be, among all of the unexplored towns, the one we know we can get to the quickest. In this case, that's town F, which we can get to in 2 minutes. And now, the two-part process of Dijkstra's algorithm repeats. We first update our estimates by looking at the towns connected to town F. It takes 5 minutes to get from town F to town G. So if we can get to town F in 2 minutes, then we can get to town G in 7 minutes, the sum of those two values. Likewise, we can get to town B in 8 minutes, and we can get to town E in 5 minutes. We can also get to town C in 4 minutes. 2 minutes to go from A to F, and then another 2 to go from F to C. But 4 minutes is actually more than our current best estimate for town C, which is 3 minutes. So we don't want to update anything here. Remember, for each town, we want to store our best estimate for the shortest amount of time required to get there. So let's keep going. The second part of Dijkstra's algorithm tells us to explore the unexplored town with the smallest value. And in this case, that's town C, which we can get to in just 3 minutes. And the process repeats again. Going through town C, we can get to town D in 7 minutes, and we can also get to town E in 4 minutes. 3 minutes to town C, plus 1 minute from C to E. That 4-minute estimate is better than our current estimate of 5 minutes, so we'll update our estimate for town E from 5 to 4. The next town to explore is town E. Among all the unexplored towns, it has the smallest value. Notice that each time we explore a new town, it's guaranteed that we will have found the shortest path to get to that town. Since if there were some shorter path, we would have explored that shorter path first because we prioritize exploring these smaller values. And through town E, we can get to town B in just 6 minutes. 4 minutes to town E, plus 2 minutes to go from E to B. So we update our estimate for town B to be 6, which is better than the previous estimate of 8. And now, the next town to visit is town B, our destination. And that tells us that the shortest time needed to get from town A to town B is therefore 6 minutes. And that's Dijkstra's algorithm for finding the shortest path in a graph. Now, there are a few things worth pointing out here. The first is that technically, our algorithm has only given us how long it will take to get from town A to town B, and hasn't actually given us which path to follow. In order to actually reconstruct that path, we'll need to add a step to our algorithm. Every time we update our estimate for a town, we should also keep track of what previous town we visited in order to get to this new estimate. If we keep track of that for each of the towns as we progress through the algorithm, then at the end, we can figure out what the best path is just by following those arrows backwards to the beginning. Also, it's worth noting that this algorithm only works correctly if the weights of all of the edges are non-negative, since otherwise some negative length path might result in a shortest path that our algorithm wouldn't be able to find. Another thing worth thinking about is how we efficiently determine which unexplored town to visit next. We want to always pick the unexplored town with the current smallest estimate, so some kind of priority queue that gives us efficient access to the next town to visit can make our algorithm faster. And that's Dijkstra's algorithm for finding the shortest path in a graph. We keep track of a distance and a previous town for each vertex. The distance for all vertices starts at infinity, except for the source, which starts at 0. And then, as long as we haven't explored the destination yet, we pick the unexplored vertex with the smallest distance to explore next. We consider all edges connected to that vertex, and if we can come up with a shorter path to a neighboring vertex, then we'll update our distance estimate and remember which town we came from. Once we've explored the destination, we have our answer. We'll know how quickly we can get to the destination, as well as what the shortest path actually is.
That's pretty sick. Same, bro. What the frick is dynamic programming? Everyone talks about it.
In many games involving dice, you might care about rolling a particular total. And as you probably know intuitively, there are some totals that are more likely than others. With 2 dice, for example, rolling a 12 isn't particularly likely. There's only one way to do it, 2 sixes. Rolling a 7 is much more likely. There's lots of ways that might come about. Here, we might ask a general question that lets us precisely figure out these sorts of values. Given n dice, each with sides from 1 to 6, how many different ways can we roll a total of m? With n equal to 2 and m equal to 7, for instance, we can pretty easily calculate that there are 6 ways to make a total of 7 with 2 dice. With n equal to 2 and m equal to 12, we might find that there's only one way. So with 2 dice, rolling a 7 is 6 times more likely than rolling a 12. It's not too challenging to work this out with just 2 dice, though. What we're interested in today is finding a general algorithm for computing the number of ways to roll a particular total, no matter how many dice there are, and no matter what the total. For instance, if we had 10 dice, how many ways are there to roll a total of 28? Whenever we're given a problem like this, it can be helpful to start with the most obvious solution. In this case, if we want to know how many ways there are to roll 10 dice and get a total of 28, we can list out all of the ways to roll 10 dice and just count how many of them total to 28. This is a correct solution to the problem. But, and hopefully you felt this way when you heard it, it's not a particularly efficient solution. It'll be perfectly fine when we're working with 2 dice, where there are only 36 possible ways to roll them. 36 here being 6, the number of possible rolls, raised to the power of 2, the number of dice. But with 10 dice, the total number of possible rolls is 6 raised to the power of 10, which turns out to be more than 60 million. That's far too many for a human to go through in any reasonable amount of time. And while a modern computer could probably make it through all of those possibilities in under a minute, if we consider asking questions about rolling 20 dice or 30 dice, it's going to be too much even for a computer. So we need to find a better way. Another common strategy for designing algorithms is to think about those algorithms recursively. That is to say, solving our big problem by breaking it down into similar, smaller problems. Remember that we are trying to figure out how many ways we can use n dice to roll a total of m. So let's start with the easiest problems of this form, where n is equal to 1, meaning we only roll 1 die. In these cases, the problem is pretty easy. For all values of m from 1 to 6, there's exactly one way to roll that value. For all other values of m, the answer is 0. There's no way using 1 die to get any total other than a value from 1 through 6. So now let's try to answer a slightly bigger question. How many ways are there to use 2 dice to roll a total of, let's say, 8? Well, a total from 2 rolls can be thought of as the result of 1 roll with a second roll added to it. And that second roll must be a 1, 2, 3, 4, 5, or 6. So for the overall total to be an 8, then the first roll must be a 7, 6, 5, 4, 3, or 2, respectively. How many ways are there for that to happen? Well, we know that for 1 die, a 7 is impossible. And we also know there's exactly 1 way for 1 die to roll a 6, 5, 4, 3, or 2. So the sum of all of these values, 5, is the number of ways we can roll an 8 with 2 dice. Maybe it seems like we're overcomplicating a pretty simple problem, and if you're thinking that, you're right, for this small case at least. But sometimes precisely describing the solution to an easier problem helps in formulating a more general solution. In this case, we can generalize and say that for n dice to roll a total of m, then the first n minus 1 dice must roll a total of m minus 1, m minus 2, m minus 3, m minus 4, m minus 5, or m minus 6. Adding up each of those 6 values will therefore give us the answer we want. This gives us a recursive algorithm for calculating the answer to our question. To roll a total of 28 with 10 dice, the total of the first 9 dice must be a 27, 26, 25, 24, 23, or 22. And how do we calculate how many ways there are to roll a 27 with 9 dice, for example? Well, that's the sum of the number of ways to use 8 dice to roll a 26, 25, 24, 23, 22, or 21. And we can keep repeating this process until we get to what we call our base case, a single die, where we know what the answer is going to be. But taking a look at the number of times we'll need to repeat this process, it seems that this strategy is pretty inefficient too. In fact, this recursive algorithm right now is really no better than our original strategy of listing out all of the possible rolls. We still end up considering every possible roll, doing exponentially more work as the number of dice increases. But if you look carefully at the process for performing these computations, you'll notice something interesting. There's a lot of repeated work. Here, we need to calculate how to make a 24 with 8 dice. And here, we calculate the same thing. And here, we calculate the same thing again. After we've calculated that result once, though, there's no reason to do it again and again and again. If only we had saved the result of the calculation the first time, filing it away somewhere organized, where we could easily access it again later, we could then reuse the result of the calculation every time we need it again. And this is where the efficiency will come from. We just need some space to store these results that we can reuse. We can use a big table, a lookup table, as it's often called, where we'll store the results of each calculation. This lookup table has 1 row for each number of dice, from 1 up to our goal of 10, and it has 1 column for each possible total, from 1 up to our goal of 28. We can start by filling in the first row of this lookup table, which represents all possible sums with just rolling a single die. We know that for sums of 1 through 6, there's exactly 1 way to do that, and for all other values, there's 0 ways to do that. Now, we fill in the next row, representing all possible sums with 2 dice. To calculate each of these, we just need to add 6 values from the previous row. And for the third row, all possible sums with 3 dice, each value is obtained by adding 6 values from the second row. For example, the number of ways to use 3 dice and achieve a total of 10 is the sum of the number of ways to use 2 dice and get a total of 9, 8, 7, 6, 5, or 4. Getting a total of 4 with 3 dice, meanwhile, requires getting a total of 3, 2, 1, 0, -1, or -2 with 2 dice. Of course, getting any total that's 0 or negative is impossible, so we can effectively throw those possibilities away and only consider the other ones. If we keep repeating this process, filling in these rows one at a time, we'll eventually fill out the last row, and figure out how many ways there are to achieve a total of 28 with 10 dice. And we did so by just doing one calculation for each of the cells in this table. It might seem like a lot, but it's much, much fewer than the more than 60 million possible die rolls that we might have gone through otherwise. This then is the principle behind what's called dynamic programming. By formulating a problem recursively, that is to say, defining a problem in terms of smaller versions of the same problem, and then using a lookup table to save the results of calculations we've already done, we can often dramatically speed up these algorithms. And these kinds of techniques are broadly applicable. It's not just about rolling dice. It's about recognizing that we can both solve new problems and remember solutions to old ones, and recognizing that by remembering what we've already done, we enable ourselves to more easily and more efficiently solve bigger, more challenging problems as a result.
I'm way too tired. See ya.